start. Thank you, Andrei.
Okay. So, dear colleagues, yeah, please.
Yeah. So good morning again, everyone. My lecture today is about cementation. It's a method of immobilization of these nasty radionuclides, which otherwise can poison the environment and the humans, etc. So it's a method of immobilization. And here it's combined liquid and solid radioactive waste. Okay, so that's the content of my lecture. So it's quite extended. I'm starting again with some definitions. So conditioning. What is the operation of conditioning? As a result of this operation, we produce a waste package. So this is the object that after that it is stored, it is transported, it is disposed of. So it's ready for disposal. We need to prepare this waste package. And because of that, we use conditioning. And then in the conditioning, it can be or cannot be the immobilization. So if you have some liquids, we need first to immobilize them to produce a waste form. And this waste form is inside of the container. So here in this slide, you see this definition of these terms following the IAEA glossary. So as a result of the conditioning, we produce a waste package. So we see that it's a container, but it's not just the container. The container, it's just the vessel where we put everything, all the stuff inside. So the waste package is the container itself. In the container, we got waste. It can be some drums, like in this picture it is shown, and then some backfilling material, some liner, something additional. So then this waste package, which from outside looks like a container, it is stored, it is handled, it is transported, and is disposed of. So we should prepare a result of the conditioning, a waste package. So these were the definitions. So immobilization can be a part of conditioning, but can be not, because if you got some solid waste, some drums, we just put them into the container, add some backfilling, maybe grout, maybe just bentonite, something backfill, and that's it. But if we deal with some liquid radioactive waste, then we need to apply additional waste immobilization to convert the waste, which in the waste, if it is a liquid, the radionuclides are in a mobile form, to convert them in a solid and stable form, and this form, it is termed waste form. And when we apply waste immobilization, the radionuclides can immobilize either via binding. We bind chemically the components of the initial radioactive waste in something, can be a glass, can be a cement, or physically surrounding, like doing encapsulation, surrounding these parts of the waste with the matrix material. We say matrix material. After solidification, the cement, it's a matrix material. So when we produce a waste form material, when we do immobilization, there are 7 important factors when we select a waste form material. First, we are looking to the waste loading. We are interested to put as much as possible waste from the economical point of view, but not compromising the property of the waste form. So waste loading is important, and we would like to put as much as possible waste in the waste form. Then ease of production. Naturally, we tend to use simple technology if only this is possible. And here, of course, cementation is something which is preferable, because indeed the technology, it's working at room temperature, not complex equipment, etc. Then durability. We need to have a low rate of dissolution of the waste form that we produce, because later on, in a far future, the water will contact with the waste form, because the container will be destroyed sooner or later. Later, of course, but if we speak about hundreds and thousands of years, inevitably will be corroded and destroyed. Then the water will be in contact with the waste form. The waste form should be durable. So number 3. Number 4, don't forget about radiation. We are dealing with the radioactive waste, decaying radionuclides, and they are going to decay all the time until the almost full decay, because it's exponential. Always you will have some decaying remnant radionuclides. But radiation stability is very important, particularly when we go to higher activity waste, intermediate and high level. Chemical flexibility. If we work with the waste, this is a complex material. The chemistry can be quite difficult. So we need to have the flexibility of the waste form so that the waste form will accommodate all these chemicals into its body. Number 6, it's important to see natural analogs, or maybe at least ancient analogs, maybe materials that are man-made, not natural, but nevertheless, if they are for a very long time in the nature, we see how they age, how they corroded, how they behave in the nature. It's important. And number 7, compatibility with the disposal environment. So the chemistry of waste form itself should be such that it should be familiar with the environment which is there. Okay, so now we move to the waste forms, and here it's a picture which shows again the classification scheme of radioactive waste as recommended by the IAEA. So half-life and activity content. But here I put in this picture not the disposal end point where the waste is going to. So high-level waste goes to deep geological disposal, right? Here I put the materials in line with the IAEA recommendations. So for high-level waste in the upper part, we got most durable materials: glasses, ceramics, metal containers. Then we go to the intermediate level waste. You see here, same, but cements appear here, geopolymers appear here. Low-level waste, cements, very low-level waste. We don't need the matrix material. We don't need to immobilize additional these materials because they are a little bit above the exemption levels. So this is a table that shows, the currently used waste form materials. So the table starts with glasses, with ceramics, with glass composite materials, which are the most durable materials, and the cements are here. But if you look on the practices, then we see that cement is the most frequently by volumetric. This is the main material of nuclear waste immobilization, because most of the radioactive waste produced by industry, by research, and so on, it is low-level waste. This is more than 90% by volume. So because of large volume of this waste, and because of the availability of the cements and very good properties, the cements are the main materials which are used in nuclear waste immobilization. And my lecture is focusing just on cements, just on cement. It's a lot of material. So very briefly, a section in line with the last questions that you asked me yesterday about retention of radionuclides. So the picture shows schematically that this time, even very durable canisters made of stainless steel, this time will be destroyed, corroded, and the water will be in contact with our waste form that we produced during waste immobilization. And then we will have contact of the waste form, because the radionuclides are not in the walls of the container. They are here in the waste form. And we will have the waste form in the water. We have some concentration of radionuclides in the waste form, and they gradually will be extracted, removed, we say leached out of the waste form. So we will get some concentration of radionuclides in the contacting water. And water is the main medium which promotes the migration of radionuclides in the environment. And I put here, most of you know that, but nevertheless, as a reminder, which is a good one. We have two parameters. The first one is called normalized leaching rate, and it is defined here, normalized leaching rate. I'm not going into the details. If you want in the questions, I can explain more, but this is not the real leaching rate. It's normalized. It was defined, and it is used everywhere to be able to compare the results from one laboratory to another. So here is the definition, and here currently we have got standard test protocols. So in Russian Federation, they are even at the level of state standard protocols, how to test a waste form, So you see here, this is ISO, International Standardization Organization, or American Society for Testing and Materials, the numbers. So there are, and here there are many standard tests. There are many activities in this area, but these protocols are standard. So if you do some research work, please use standards. Otherwise, your results, how to compare them with the other results. Maybe you produce something fantastically good, but no one will believe to you because it's not following the testing protocols which are internationally approved. So this is the table. And again, a reminder, in reality, when the water contacts the waste form, the leaching rate is not the normalized leaching rate. No, it is a real one. You should multiply the normalized leaching rate which you obtain through test protocols with the concentration, specific concentration of radionuclides in your waste form. Because of that, instead of this very small number, you'll get another one which is much, much even smaller. So here it's a summary. If you look to different waste forms, so let's say you take as a waste form some cements or some calcine. So you just calcine the salts and maybe they are enough durable. So you see here the leaching rate, normalized leaching rate is quite high. The cements, bitumens, phosphate glasses can be even more durable than borosilicate glasses and ceramics. Of course, thin rock is the most durable ceramic, but some of the ceramics are not durable at all. They are even worse than cements. If there are some water-soluble phases in ceramics, then the job is not done by ceramics. That's why the glasses practically are frequently used. They are industrial use compared with the ceramic, which are more durable, can be more durable, but are not yet used industrially. Okay, so we move to cements. So here's the definition of hydraulic cements. So these are the materials that solidify if you mix them, powder of these materials, with the water in normal conditions. And here, two things, just to be about the definitions. So if you have cement without just cement and water, or with some fine aggregates, this is more time. But if you put some gravel, then you got concrete. What is that? Okay. So what are the advantages of immobilization by cementation? So 7 again things, 7 aspects. It is simple, low cost processing. You work at ambient temperature. You don't need high temperature, you don't need low temperature, normal temperature. It's suitable for a wide range of the waste materials. So sludge, liquids, emulsified organic liquids can be cemented. You have some oils, you make a emulsion and then you cement it. It's also a method. Good. Number 3, thermal, chemical, and physical stability of the waste form. It's a durable material. Look around the buildings. Look around. In the city of Moscow, you have the television tower. It's a half of a kilometer tall. And you think it's made of ceramic or granite. No, it's made of cement. Half kilometer high. You imagine the durability of this material. And it is standing there for all my age, let's say. So it's there. We have rains and rings and so on and so on. Alkaline chemistry, I put here in the slide in a red color to pay your attention to. If you speak about cements, it's a lot of pore water in the cement. And if you take a sample from this pore water, micrometer size, but the water is there in the pores of cements, everywhere. The water is alkaline. It is good or bad? It is very good. It is very good first for let's say iron, because it does not grow in alkaline water, but it's very good for radionuclides, particularly actinides. The mobility of actinides in alkaline solutions is extremely low. They are immobilized already by the chemistry. So it's a good chemistry. Non-flammability of the waste form, good self-shielding, so radiation is shielded, which is also good for us. And good, even a very good compressive strength of the waste form, and that facilitates handling. So a little bit about how they are produced. So let's say Portland cement, you take some clay minerals, you put in a furnace, you burn all this stuff together, then you produce nodules, you produce powder, and the cement is ready for solidification. If you look on a typical composition of the Portland cement on oxide basis, you see the number of oxides, many of them, the average, the maximum concentration of oxides is given in this table without comments, otherwise no time to speak about. So basically we have in form of oxides 60-65% of the lime, 21-24 silica, 3-8% alumina in Portland cement. Pay attention. And ferric oxides 3-8%. And other things, it's shown here. Now, because of the variety of the oxides, In the cement chemistry, instead of writing, all this long chemical formula, we use abbreviations, and the table explains you the abbreviation. So C, it's not carbon. In cement chemistry, C is oxide of calcium. And then S is not sulfur, it's silica. It's silica. And then A, it's alumina, and etc. So later on in my slides, you'll see these abbreviations, which are frequently used, are everywhere used when, and if you look about the paper about the cement. But these are not oxides in the cement powder. They are actually minerals. Minerals. What are the main minerals of the cements? Portland cements. Portland cement-based cements. So the first one is a lime. You see here, it is calcium silicate. It is also called yeelimite. Yeelimite. So calcium silicate or halite, it's the name of this mineral. Then you got calcium silicate, which is belite. You see here, it's silicate of calcium. So, but it's decalcium silicate actually. The halite is calcium silicate. It's different. And then you got aluminite, and the abbreviation is 3,3A. And so on. You have this, and you got lime, calcium oxide, and a little calcium sulfate. Now, if you look to the properties of this Portland cement mineral phases, they are different in contact with water. So halite, rapidly it's hydrated, has high initial and final strength. If you take just halite, nothing else. If you take just belite, you see it's slow hydration. If you take aluminate, it's even very rapid hydration and high heat of hydration. And ferrite, slow and moderate hydration, moderate heat of hydration. Due to the hydration, we have release of some heat. So the reaction is exothermic, right? Now we move to there are many cements. So let's say in former Soviet Union that I started with my career there were about 48 or something like that standardly produced cements industrially, on large scale, and there were conditions, exact composition of these cements with some variations, but nevertheless. I put here the British standard. So we see here 5 types of cements, and their composition is specified in this standard. The same it's in Russian Federation, and I guess in your country. But in United Kingdom, let's say we use the European standard. But nowadays, because of the Brexit, this stupidity, I'm sorry to say, yes, of the Brexit, it's again British standard. Nevertheless, it's the same content of the British standard. In the United States, we got ASTM standard, American Society for Testing Materials, and you see here the 5 types of the cements. The table very useful one because look, in the table we got these minerals, so halite, belite, and calcium aluminate, and aluminum ferrite, calcium aluminum ferrite, and others. And if you take type 1, you see here the content of these minerals. And the first one, type 1 cement, is general purpose. This is OPC, ordinary Portland cement, general purpose cement, with no extenuation conditions. Then type 2 aids in providing moderate resistance to sulfate attack. And look, the composition is different. It's little content of the calcium silicate. It's more content on decalcium silicate, and so on. Type 3, when we need high air strength. So we repair a road, let's say, we need as quickly as possible to do that. So then we use type 3 cement. When we manufacture very large, bulky pieces made out of cements, then we take type 4 because it has a low heat of hydration. And if the structure is massive, some large buildings, basement works, and so on, type 4. And if it is working in a high sulfate content waters, seawater, let's say, we will take type 4 cement. So these are ASTM type cements. So here is the description, the things that are very briefly contained in the previous table. Sorry, I'll go quickly, just the text is here, the description of these cements, type 3, and type 4. Already I noted briefly the most important things. So summary about our business, radioactive waste immobilization using cementation. So Portland cements type 1, 2, and 3 normally used in radioactive waste immobilization, normally. But there are conditions when not so normally. Let's say we are dealing with some acidic, let's say boric acid. It's typical in nuclear power plant. In nuclear power plant, liquid radioactive waste. So what to do? Because these cements will not work. Then maybe we need to add some additives or to move to other type of cements. So once again, we say cement, but it's a range of cements. It's not just one. So here are the additives. So what do we use in different? So this is modified Portland cements, and they are used in waste immobilization. For your information, so if you need to adjust the pH, if you work with the boric acid waste, you add some lime, and then the business is done, and so on. You see here, we can add some pozzolanic materials, reactive silica, or some slag, and then we can work with other waste streams. Here it's in terms of oxides. Where are these additions in terms of the oxides? Not stopping here, but need to note to you, because that was under IAEA, a coordinated research project, which combined researchers from the entire globe, let's say, and we looked on the alternative cements under development in different countries, to immobilize radioactive waste, because it's large amount of radioactive waste that, and then depending on the situation, alternative cementitious compositions are developed. So these are calcium aluminate cements. So that you see they based on clinkers of used products with decalcium silicate and calcium aluminate, right? Or can be calcium sulfur aluminate cements, or can be magnesium phosphate cements. These are often termed ceramics because they are very different from cements. The reaction is acidic. You need acidic composition to produce this so-called ceramic, or maybe it's taken by the way it's borrowed, let's say, from medicine and from other industries, because in dental practices, this kind of ceramic, it is used to manufacture, replacement of our teeth when they are destroyed. So it's a very durable material, really. And geopolymers, maybe you heard about geopolymers. Geopolymers look like cements, but much more durable, and a lot of work is done in this area of production of geopolymers. A little bit of hydration reactions. So when we mix the cement powder with the water, let's start with just the water. Look to the chemistry. Then we have this interaction. So I put in the slides the chemical reactions. The heat liberated, the reactions are exothermic. A lot of heat is liberated. So if you have a massive drum 200 liter and a drum 500 liters, the difference can be such that in 500 liters, the temperature can go up to 100 degrees and things will start boiling. So need to be careful with the cement. And the information it is given here about these reactions. And physically, if you look, you have initially the powder. So each grain is a mixture of these minerals. So this is the cement grain. This is a mixture of the minerals. So it's the light, everything together here, and the water. But then gradually, the cement start to harden. So interactions occur, these chemical reactions that just they're demonstrated to you. So other hydrated phases are growing here, and they grow and grow and grow. So finally, we have something, these pores inside. So something, these pores, look here to this slide. Initially, cement, powder, and water. And finally, we have some remnant unhydrated cement. Not all the grains were fully reacted. We have solid product of hydration. We got some gel water, some capillary water, and some empty capillary pores. This is just air there. And if you look to the porosity of the system from 100%, it goes down and down and down. So here's the time. Initially, if you mix the water with the cement, there is a dormant cement powder. It's a dormant period, nothing happens. Then there is setting time during hours, and then hardening days. You need days to obtain a real durable material. And in standards, typically we have 28 days. Only after 28 days, you can take a sample and measure the durability and etc. of these things. And here are the growing phases. So that one, it's Portlandite crystalline phase, very important in cements because it keeps alkaline conditions in the port water. And CSH phase, which looks very like as a glassy phase, amorphous phase. It is called tobermorate, calcium silicate hydrate, CSH phase. So it's considered as the most important. So here how these phases are formed. The hydration, here it's again about the strength, about the amount of heat generated, reaction rate. So you see here the fastest, moderate, slow, how they interact, and degree of heat liberation. Important. So after all, after 28 days, we can look what we obtain, the cement stove. And here it's the mineral name. So this is not mineral, this is so-called CSH phase, it's amorphous phase. It's representative formula, chemical formula. This one is Portlandite, it's crystalline, CH notation, so it's calcium hydroxide actually. This is ettringite, the notation, the representative formula, and crystallinity here. You see, so these are fully crystalline phases. This is high medium, hydro garnet or hydrocaluminite, and again notation and a chemical equation. Since we have not just cements, but very often composite cements, so in United Kingdom, we use the blast furnace slag cement, a mixture. This OPC, I put here and put even the arrow to indicate the pH of the core water. And this is after 28 days. Very alkaline solution, which is good. And the hydration products, they are not the same in composite cements. And again, depending on the cement that you use, then you will get, and you need to analyze in order to know exactly the mineral phase of that you obtain. So if you look into the microscope, it's our British composite cement. So this is blast furnace slag particles inside, and the cement is surrounding all these particles. And it's after 90 days cured at room temperature conditions and water to cement ratio, and here about the composition of this material. So summary, what we obtain after hydration. So 95-98% in the internal structure after even 1 year, it is hydration reactors finished. But in reality, if you take even an ancient cement, a very old one, 1,000-year-old, even there we can find some unreacted particles, very minuscule, very small, and identify what the ancient people worked with at that time. You know how it's useful to know nowadays then. Yes, okay. So here it's also information about the pores. So if properly the water to cement ratio was used, technology was obeyed, then the pores are small in size, and in these pores we have got some remnant water. Useful for characterization. So here, if you look thermal analysis, you can look at the reactions of dehydration, and on the peak in this thermal analysis, you can identify the phases. So without even X-ray analysis of the material. So let's move to the technology. Now we move to the things how they are used in a technology. When we work with the radioactive waste, we can use just water, right? If you have some solid radioactive waste, some metallic pieces, we need to grout them to put them in cementitious material. Then we can use just water. But most often we are dealing with the liquid radioactive waste. So in the making concrete, more water typically is used and required for hydration stoichiometrically. In doing nuclear waste immobilization, in applying cementation, we also are interested to use more, not water, but liquid radioactive waste, because waste loading is then higher. But need to be careful with that, because if you put too much water, too much liquid radioactive waste to interact with the cement, we will obtain a not good quality cement stove. And this plot illustrates that. So this is the water to cement ratio, and we move to 0.5, 0.6, and so on. And this is the conductivity. So the material which you obtain is porous material. And if the pores are large and many pores, then the conductivity, how following the Darcy law, the water will pass through the material. And if in the future the water will pass through our material, it will take from there our radionuclide, so it's not a good thing. So here you can look to the conductivity of cement paste. Immediately after we produce this, the conductivity is very high. So the water passes like a sieve there. It's moving slowly, but it's moving. But with time, so you see here ultimate conductivity of the cement. Conductivity, sometimes permeability is used, which can be calculated using conductivity and density and viscosity, and is measured so this is meters per second, and this is square meters. How to recalculate that? Because in the paper you can find just permeability of the cement, cementitious materials and rocks and so on and so on. You see the ultimate conductivity is small. That's it again, how these things are developed. And again, if we are cementing solid materials, not much interactions occurs in between the waste material and the solid materials, apart that some situations can. So in United Kingdom, when we cement Magnox waste, it's magnesium, aluminium, alloy, and it interacts with at high pH water, we have generation out of the hydrogen, but typically iron and ferrous materials, so and so on, there is practically no interaction. But if you work with the solutions, then we have a lot of chemistry, because these are solutions. So we should carefully look on these chemical interactions. And here a kind of, you know, how the cations and anions interact when we mix them with the cementitious paste, so water and cement powder. And we need to consider these reactions, and this is the table that gives, you know, so if you got soluble borates, some lead, some zinc, then the reaction is precipitated salt, which can coat the cement grains and impact the hydration reactions, and nothing will happen. The cement stone will not be produced. And you see other nasty, so flocs are produced, yesterday I explained to you, in water purification, and they can contain a lot of ions there, and they also can retard hydration. You need to be careful with that, and so on. And because of that, in cementation technology, to overcome these deleterious interactions, we are using additions. We add modifiers to the cement when we produce this cement grout to cement the radioactive waste. And you see that we are using polar high molecular weight. They are called superplasticizers. They are known well in cementation, in cement industry, in production of the buildings and other things made out of the cement. So they are called superplasticizers. They are reducing drastically the viscosity, and we need low viscosity when we cement the solid radioactive waste to fill all the gaps in between the materials. And you see here for other, the table gives you the generic information about the additives used in cementation technology. Now, we have two types of technology. The cementation when directly in a drum, the mixing of all the stuff it is done, and when we produce the mixture in a dedicated mixer, and the final product is then discharged into a drum. So this is the first one technology. So we go to the cement bin, maybe this additive, maybe this. We have here the waste feed pump. We put everything into a drum. In the drum, we got the propeller, the mixer, which does the business. And here, example from United Kingdom. So we have here in drum mixing pedal, you see here, and this so-called sacrifice. So after the mixing there, it remains there. Nobody is taking it out from there, and it's a part of the drum, which is then moving to the package to be stored and disposed of. Or can be like in this photograph, in the mixer, which is put into the drum, is mixing then, and then is removed from the drum, and it's used for the next drum. And so that it's shown technological unit that is doing this kind of, and also we can use here additives and also put them additionally to the waste, the water, and the cement and you see here the waste, the water and additives that I just noted to you. And the second type of technology, it is when, look here, we have a dedicated mixer, and in the mixer we produce this mortar or most often. So it's a grout which contains all the components which further will solidify inside of the drum. And the drum can be even put on a platform which can be shaked, vibrated, in order to add here inside of the drum some solid waste. Then we will combine, we will solidify together liquid radioactive waste with solid radioactive waste. And this is a technological scheme, a real one, which is applied that is from Russian Federation, from an organization some 75 kilometers from Moscow, with the name Radon. Mikhail Polkanov from this organization will give you today a lecture on thermal treatment technologies. So you see here inside of the drum, we got solid radioactive waste, and the liquid radioactive waste are already in the grout, which is put here, produced in this mixer, and then everything solidifies inside here. But that is put on a table, which is shaking, is vibrating. And in such a way, all the gaps are eliminated, and we have a good quality material produced. And this is very often used, that kind of the technology. So this is the real photograph of the unit that I just, the technological scheme demonstrated to you. And this is a mobile, this is a unit, it's a transportable unit from Georgia, a very small capacity one that I delivered when I was the technical officer for Georgia, working for International Atomic Energy Agency. These are things from United Kingdom. So we solidify the solid radioactive waste in 500 drums, you see here, and both liquid and solid radioactive waste inside of low-level waste, of course, inside of this is intermediate level waste, inside of large ISO containers. So we care here about the heat generation during the solidification. This is again a photograph taken from Georgia. This is in Caucasus region, nowadays independent country, and you see recently we published a paper. This is my name here, so it's freely accessible. You can look on all this stuff there. So durability of the cements, it's very important, and is in line with the yesterday question. You see, not everything is accepted. So there are acceptance criteria for the material that we are producing, and in a Russian Federation, these requirements are at the level of state standard. So you see, from state standard, there is a requirement that the waste form that we are producing should have, I say must have, the leaching rate not higher, less than 10 to -3, normalized, not the real one, normalized, in gram per square centimeters per day for cesium, the most mobile radionuclide, you see. So if it is higher, no, it's not accepted. It's against the law. You need to remanufacture, to do everything again. It's not accepted. And the same is everywhere. We have requirements. The material must be enough durable. Otherwise, indeed, it can this time poison the environment. Then the durability, mechanical durability, the compressive strength must be higher than 4.9 megapascal. And you see here radiation durability, freeze durability, durability long-term water immersion. So this is taken from Russian Federation at this level of state standard. And Europe, this is from Italy. You see again the requirements. So it was almost the same. So in United Kingdom for mechanical durability, we got 10 megapascal, but in Italy is the same like in Russia, 4.9, 5 megapascal. In France, by the way, for the waste form is 0.3, and is also normal. We don't need very high mechanical durability of the waste form, because the container it's keeping everything aside from the mechanical point of view. And all kinds of the requirements and test protocols used to prove to the operator of the waste disposal facility that the material that is brought here, it's in line with the requirement. Things should be accounted that the water in the environment, it's not, ionized water, can be aggressive one. And then the cement paste, the cement material, the cement stone will start to degrade. That happens very slowly, but nevertheless, inevitably will happen. The information that we have during the testing, during the field testing of the cemented radioactive waste prove that if the technology it is obeyed, it is done as designed, then you see here that this is a photograph. It is, by the way, the work that I'm also, I was even the leading expert in doing this work when I was working in Russia for 20 years. So we opened one of the testing mount type repository with the cemented radioactive waste from nuclear power plant. And this is not a fresh photograph. This is a photograph after 40 years. So 40 years, these are the blocks that look like new, just be replaced in there. You see, they look very well, very well. So we investigated, we have publications with my colleagues from Russia about the decomposition, about the change to occur, of course, inside of the material. Bleaching is very slow. The phase composition is that one that is proving the very good quality of the material. And that is increasing our confidence in cementation technology. And of course, the availability of ancient materials made out of the cements also gives additional information. So you see here the photographs of very, very old, thousands of years old. So the Great China Wall, everyone knows it. Maybe not everyone knows that in the United Kingdom, there is a so-called Adrian Wall, which was built about 1000 when the Great Britain, the British island was conquered by the Romans. So they built a wall from the sea to the sea to separate the upper parts, Scotland actually, yes, from the lower part. So it's like, Great China Wall. Why was built? Because they were defending themselves from Mongolians, from the tribes that were living there. Yes. So here the Scottish people were more aggressive. So about the materials. So we can look to these materials. The walls are still there, more than thousands of years. So remnant materials are there, and it was even an old Roman law which required that aqueducts should resist at least 200 years. They ensured lifetime. And we see in France, the photograph is from France, the remnants, and in Italy, you can see these photographs of aqueducts. So these materials, cement-based materials, are still there, and we can see that they survive in the environment for many hundreds of years. So conclusions. Cementation is the main immobilization technology for low intermediate radioactive waste, and cementitious waste forms are durable materials which provide a high degree of environmental safety for low intermediate level waste. And I put here a reference. I published with dedicated cement experts, Professor Rakimov and Rakimov from Russia, by the way, from Kazan University of Russian Federation. You see also my name in this monograph. It's published by Wiley. It's dedicated to cements and cementation technology for more information for the people that are working in this area. So, dear colleagues, many thanks for your patience that are here with me. Let me stop sharing. Stop sharing. And let me also greet my colleagues from Argentina. A couple of people are here from Argentina. Sorry, I'm greeting everyone, but greetings to my colleagues from Argentina. It's my pleasure. Yesterday, Ariel Chavez was online, and Aileen Manzini was online. You were, of course, online. So greetings to everyone. It was my honor to work with you for many years during my term in International Atomic Energy Agency in Vienna. So it's my pleasure to see you again, and greetings to all my colleagues in Argentina, really. So thank you, dear colleagues. Maybe some questions to me. I have a couple of minutes or something like that. Yes, 1 minute.
Thank you very much. So, please. Okay. Some questions? Yeah.
Yes. Hello, sir. I have two questions. One is based on your lecture of yesterday's class. Uh, Yesterday, you mentioned that you have a paper written on the self-disposal options of waste. I would like to know why was that not implemented, that strategy?
That strategy and proposal started to be developed many years ago, and this idea well developed both in the United States and the Russian Federation. Perhaps the Russians were the pioneers, but nevertheless, it's not known only in Russia, this proposal. It looks very difficult. It looks dealing with the highly radioactive materials, and the industry considered it too complex to be implemented. And it is only for a very small fraction of radioactive waste, which is really very highly radioactive. So the bulk of the waste is cemented, like I explained to you today. So the industry didn't decide to put, the funds here, but to note to you, because in 13 years ago in Washington, there is an international project on a deep ocean drilling. The people want, from the scientific point of view, to drill to get to the mantle. So they invited me from Sheffield, to be involved. But again, it was a big interest to this capsule, to this self-sinking there. But when we applied for funding to the National Academy of Science of United States, we couldn't pass, the peer review. So the people considered the safety. You need a huge, shielding, very high level of radioactivity because of this high danger of contamination and so on and so on. So other experts consider this project with high, skepticism, but that is difficult to implement. By the way, we don't know about our Earth interior. We know more about the Moon and Mars rather than what's happening, under our feet. So that is the reply.
And sir, the second question is based on today's lecture. You've told that in cementation, the target is to have the radionuclide immobilized in the cement matrix. So are we looking at a homogeneous cement matrix, or can it be a heterogeneous form of a matrix also, wherein the radionuclide can be a heterogeneous part, not properly mixed with the matrix?
Yes. So the correct answer is the last one that you noted. Heterogeneous matrix is allowed and is the case practically everywhere. So if you speak even of cementation of liquid radioactive waste in the United Kingdom, we are using composite cements, this blast furnace slag. So already this slag, it's producing a heterogeneous material. I saw you some picture, some photographs. You saw there are large particles. They are seen in optical microscope. We don't need the electronic microscope to see them. So heterogeneity is allowed. It's allowed for cementation. So don't worry about that. The requirement is to have the properties of the whole waste form such that the leaching is very small, the durability is high, all the things that are aligned in the state standard in Russia, in requirements in other countries. Heterogeneity is allowed everywhere. I can tell you things that you are not asking about. Even for vitrification, vitrification means production of the glass. Yes. Some heterogeneity is allowed, even on distribution of radionuclides, which is limited, of course, in vitrification, but nevertheless, it's still allowed.
And sir, what are your thoughts on these new techniques wherein synrock is a technique that is being researched upon, or transmutation by accelerator driven systems? Do you think they are feasible, or would you still stick to immobilization by cementation?
The participants, I should inform you with a very good news. It's announced for many years, but doesn't happen. But most probably will very soon. In Australia, they are starting testing of parts of a plant which is going to use synrock type materials. for immobilization of radioactive waste. And this is not a transmutation that you just noted, but maybe in the future will be for transmutation as well used. But I mean, there are great progresses in industrial application of ceramics, thin rock-based ceramics. So the Australian in Australia, they will start to do that. And it's very important for everyone. Why? Because this is the first example in the world when the ceramics, more durable materials, are going to be put on industrial, scale to be used. And then other countries, the things are happening in such a way that if someone started to do, is successful, then everyone follows. So the French started to beautify, and then, the Russians started to do that, the United States, they started to do that industrially. The research is done everywhere with this enroll, but industrially only in Australia, they are going to do that soon.
Thank you, sir.
Thank you very much. Some more questions? No? Okay. Yeah.
Thank you for your presentation. I ask about which cementation we can use, from which country it is can get better to waste immobilization or nuclear waste immobilization. Is it from, for example, from India, or which manufacturer or made in which country can use for nuclear waste immobilization? It is better than from another.
Cementation is used practically everywhere. So for some simple cases, if you speak, let's say, about the immobilization of sealed radioactive sources, it was a part of my yesterday lecture. Then very simple cements that are commercially available. You don't need much. Of course, again, you should look, what kind of the cement you are going to use, because there are many. But nevertheless, the situation looks much simpler. This is solid radioactive waste. There are no effects of interaction of the material with the cement. We just encapsulate everything into the cement. So once again, cementation, it is used practically everywhere as the simplest approach in immobilization. It's on a very large scale used by nuclear powers, of course, and it started to be used from the very beginning, so many tens of years. So if you want some advice on cementation, since you are now in Moscow State University, you have so many very good experts in cements. I noted to you two of them. I took them as a course of the book that we published. But there are so many cement experts that are accessible in Moscow and so on. You can ask advice from them and you will get. And once again, if you have a large program, you can ask IAEA. Again, they will provide you assistance in more complex situations. So for cementation, the overall approach is not a difficult one. There is so much experience that you don't need to be specific and to go certainly, let's say, only to England or only to the United States or only to India. You can go everywhere where there is practice, and the first is to stay in Moscow and to ask your colleagues from Moscow State University. They will put you in contact with the relevant people.
So we can say pure cementation, we can use it. No need to mix with another thing, just pure cementation.
It depends on the waste. It depends on the waste. And there are generic advices given in IEA technical documents. You can open and follow these, but then if you get on some problems and difficulties, you will go deeper and look to the book and so on. So I cannot say that always it's a simple question, because if for example, if you have spent ion exchange resins and you try to solidify them using cementation, you very soon will see that it's not so easy to do that.
Thank you so much for your answer.
Yeah, one more. Yeah.
Okay, I want to ask, are there more areas of extensive research on cementation for maybe spent nuclear fuel like this, maybe cement?
the cement, the cementitious materials are indeed barrier materials even for high-level waste, but these are basically barrier materials or containers. Because if you speak about spent nuclear fuel, then you have large containers, because you need very good shielding, and they are also manufactured based on the cementitious compositions. That's something very different from the things that I just in my lecture gave to you, because it was mainly about cementation of low-level waste and liquid radioactive waste. And high-level waste is not cemented. You cannot do that, because the radioactivity is so high that the cement is not enough durable. First, second, it can undergo radiolysis. The radiation in high-level waste is so high that radiolytic reactions are going on a very high rate, and so on and so on. So there, for high-level waste, in my first slide, I indicated to you, for high-level waste glass, cement, it was not there. Cement is not there. Cement for high-level waste cannot be used as a matrix to immobilize this waste. Durability is not enough, and it decomposes, and so on and so on. So no. But for spent nuclear fuel, containers are made out of cement-based materials, and these are, like shielding materials around the spent fuel. But then, if you go to the disposal, you may pay attention, like in Sweden, where in Russian Federation the spent fuel is reprocessed, is a useful material. But in countries like Sweden, the spent fuel is considered waste, and then they are going to put the spent fuel in canister made out of copper, not cement, copper. There are inserts made out of steel there, but again, it's not cement. So don't confuse these things.
Okay, thank you.
Thank you very much.
Oh, I see online Ariel Chavez.
Yeah. From Laura, yeah. So we have one question from Laura in the chat. I would like to ask if you know alternatives to cementation for ion exchange resins, and you think about pyrolysis.
Even I noted that ion exchange resin is a troublesome waste stream. Yes, geopolymers are already industrially used, so approved by regulatory authorities in Europe, in 2 countries at least. They are considered in many places, so not only 2 countries, but in Czech Republic and in Republic of Slovakia, here in Europe, in the center of Europe, they passed all the tests, geopolymers as alternative to the cement. And the advantage is that they accept more ion exchange resins. For immobilization, they are less sensitive to these chemical things, swelling, all these nasty things. So geopolymers are real good alternatives for cement. But thermal treatment then does you decrease the volume, you decompose all the organics, you do a very good thing. So thermal treatment, it's something, but it's more complex. So, but of course, the advantages are so significant that if you have large volumes of ion exchange resins, then pyrolysis or other thermal treatment, you will get some ash, and then this ash can be liquefied, can be produced in ceramic, and so on and so on. So that's something really not just alternative, but much better alternative to cementation if you speak about ion exchange resins. And very typically they are intermediate level based, so it's a good thing to do this.
Thank you very much. So thank you. Let's move to the next lecture. Thank you very much, Michael.
Okay. So
see you.
Can you hear me? Oh, very good. I hope that you like staying in Moscow and these summer school classes. I will speak about advanced techniques for material characterization, especially for radioactive waste characterization, basic principles and application. My name is Irina Vlasova. I am from Lomonosov Moscow State University. We will speak mainly about legacy, historical radioactive waste, because in that case, you don't know what is the composition of radionuclides, what is the matrix, what is the inventory of radionuclides, and what is the speciation of them. If you have recent waste, it is not a big problem to know how to manage them, how to can make a conditioning of this waste. But in the case of historical, it is a problem. So the first point of this lecture is, what is it, legacy waste sites? And then we speak about general classification of non-destructive techniques, namely about autoradiography, electron microscopy methods, Raman scattering, and X-ray method. Legacy waste is very complex, heterogeneous objects, and it is a problem how to manage them, because radioactivity could be distributed not homogeneously, and you are to find these spots and to understand what are the species of the radionuclides, how to manage them. That is why it is a question what kind of methods you are to use, because there are a lot of methods. We have not so many time, so some of the slides I will miss. The general classification of the methods is there are three big groups of the analytical methods. The first is the imaging and visualization methods, like X-ray methods and electron microscopy and some other, when you have image of your sample. The second group is spectroscopy methods, when you have the distribution on energy of the signal from your sample. And the third group are diffraction and scattering methods. If you try to find the general classification, you can divide your methods to passive techniques, those who are excited by photons, like X-ray or laser sources. The third group are methods which are excited by thermal neutrons, and the next group by electrons and charged ions and multiply charged ions. You know about passive techniques. All radiometric methods are passive because they are used for radioactive materials with some decay, with some radioactivity. And in some cases, it is not enough. You are to use some excitation sources. Let's go further, because I have not so many time to discuss everything in details. The first method we use is radiography, because we can reveal the heterogeneity or homogeneity of your sample. Sometimes you have homogeneously distributed radioactivity, and in that case you can analyze bulk samples of your waste. But in some cases, it is not the case, and all radioactivity could be concentrated in some local spots. In that case, you are to use some micro-local analysis and use another techniques. And if you have a lot of huge amount of waste, you can analyze only some small amount of them. So it is very important to choose this proper preparation of your sample, of your waste. So about radiography, there are a lot of different kinds of detectors in radiography analysis. All of these detectors are sensitive to radiation with special resolution, not for bulk analysis, but with some special resolution. The most the first kind of detectors are X-ray films, photoplates, and nuclear emulsions. You know that radioactivity was discovered using X-ray, using photoplate. It was very first usage of discovery of radioactivity. And the second kind is solid-state nuclear detectors for charged particles. And another type of detectors are imaging plates. They are used in medicine and in science. In our case, we use autoradiography with imaging plates. It is storage phosphor screens, which could reveal the distribution of radioactivity in your sample. The other kind of detectors are detectors in real time. They use mostly in medicine and biology, but sometimes in radiochemistry too. So we use these two kinds of detectors in our practice. Let's go. Autoradiography with imaging plates could optimize sampling processes. The fact is that destructive methods of radioactivity analysis needs very small amount of material, and radiography could help you to choose the proper representative sample. And autoradiography with imaging plate could help you to detect hardly determined beta emitters like radiocarbon and strontium-90 and some else. What is the storage phosphor screen? It has working side, blue or white, and black side. It is the support, plastic support of this sensitive layer. Exposure of imaging plates, they are placed in close contact with the radiation source, and europium 2+, which is inside these crystals of sensitive layer, is ionized to metastable europium 3+, and radiation energy stored in bromine vacancies. And well, here it is, the scanner, laser scanner with the source, laser source, which could help you to reveal the image, radiography image. The steps of the radiography is you have the imaging plate with the sensitive layer, and after some exposure time, you can have the latent image inside this imaging plate. And after laser excitation, you can read this image. And the very good fact is that you can, using visible light, you can clean your imaging plate and use it again for many, many times to erase the image. The next slide, please. Thank you. This is the example of application of imaging plate radiography to search some hot particles in the sense of nuclear testing local place in Semipalatinsk testing site, Kazakhstan Republic. You can see that we use the grid with cesium, which could be seen in your samples and could help us to find the place of the most interesting spots. It is radiography image, and this is photo of the preparation. And you can localize the most concentrated spots of the radioactivity. Doesn't work. Oh, thank you. The next example is from Angarsk electrochemistry plant, which this is the sample of the soil near the plant. And the fact is there are a huge amount of soil, but the radioactivity is very low. We are to find the most radioactive particles to try to manage with this low active waste. So autoradiography helps us to find the groups of the most radioactive particles in this. The next slide. This is the example of using of autoradiography imaging plates for revealing the contamination radioactive particles in the filters from aerosol material from not far from Chernobyl nuclear power plant. You can use different diameter filters with different pores diameter and find the hotspots in this place, please. Next one. And the very convenient thing is that you can localize particles and then make some cut the wipe, displace the parts, and each of your actions you can control using these radiography imaging plates. The next slide, please. A very interesting example is from France. They use imaging plate, a lot of imaging plates to find the contamination spots in the big building. And the fact is that this is the building for dismantling, but it is very hard to find the contamination spots because they are not gamma active. So you cannot use your dosimeter or something like that. And they expose a lot of imaging plates and find the spots which are in orange and red color on this picture. So the size of this wall was around 2,500 square meters. So it is very big place. And they found some small spots for managing of this waste. The next slide, please. Alpha track radiography is the other type of radiography analysis. The advantage of this method is that plastic alpha track detector cannot reveal any gamma or beta sources, only alpha activity. And the fact is that in the most radioactive waste, you can find different kinds of radioactivity. And alpha activity is not so high in those today, but if you are to think about the future, you know that the most of alpha emitting nuclides are very long-lived. So we are interested to know what is the distribution of alpha activity nuclides. So the next slide, please. And the other advantage of this method is that we can reveal the energy of the alpha particles if we analyze the traces of these alpha particles in the detector. The size and some parameters of them can show you what kind of radionuclide is in this sample. The next, please. So alpha track radiography is a very useful instrument for characterization of alpha emitting nuclides, especially on the background of high beta activity. The next, please. The next block of our methods are electron microscopy techniques for waste characterization. Maybe you know these methods. It is scanning electron microscopy, transmission electron microscopy. They have the general principle is the same. So it is the incident beam with high voltage, but the acceleration voltage is different for SEM and for transmission electron microscopy. You can see an order of magnitude is the difference between them. So in the case of SEM, you have a sample which is not transparent for the electron beam. You can see backscattered electrons and secondary electrons and characteristic X-rays. And in the case of transmission electron microscopy, the sample is very thin. It is just some nanometers or angstroms of the materials. It's very thin sample preparation, and the electron beam goes through the sample. It is direct beam. It is not interesting for us, but we have elastically scattered electrons and inelastically scattered electrons and so on. And all this information could help us to understand the different characteristics of the sample. The next slide, please. So the first characteristic is morphology of your sample. And this morphology can show you the source of the waste. In some cases, it is unknown, and you can characterize the radioactivity in terms of the source of contamination. Here, it is the example of a nuclear test site soils. You can see that it is melted surface. The next slide, please. Here it is the example of Chernobyl particles. You can see the grains of the initial fuel with some fission gas bubbles and channels, intragranular and between the granules of these fuel particles, fuel grains. The next slide, please. And this is the example of the particles from bubble basin from Chernobyl nuclear power plant. You know that some part of Chernobyl lava came to the water and formed the matter very close to lava when it goes from volcano to the sea. There are big bubbles inside, and here you can see some uranium oxides, monocrystals, dendrites, and very big bubbles. And you can see some secondary minerals of uranium, which was formed after many decades of existing inside this nuclear power plant shelter. The next slide, please. And the next. Thank you. SEM has two different modes for revealing different kinds of characteristics of the matter. If you use secondary electron mode, you can reveal the morphology of your sample. If you use backscattered electron mode, you can see composition. It is the same place of the preparation, but here you can see that it is heavy metal, it is uranium particle, and there are some clay minerals and some other minerals of the soil, and this contrast, that contrast could help you to search heavy metal particles in the sample. The next slide, please. And this is the composition of particles in the soil, contaminated soil. You can see that there are, according to the morphology, there are some new secondary minerals which were grown from the solution inside this contaminated soil, some precipitated crystals. The next slide, please. Except morphology, you can reveal the composition of your matter using energy dispersion X-ray spectroscopy or wave X-ray spectroscopy, and you can, so it is just the composition of your matter. Using diffraction in the case of transmission electron microscopy and SEM, you can understand the phase composition of the matter if you have diffraction pattern, and you can make elemental mapping, which could help you to find the composition inside this sample preparation. The next slide, please. The transmission electron microscopy, it is a unique tool to find very high resolution, spatial resolution images. You can just see some channels, atomic channels, some atoms of your matter. Here it is the example of a hematite, big hematite crystal with some plutonium oxides on the surface. It is model experiments to see what is the behavior of plutonium in the presence of hematite. The next slide, please. So the next, yeah. So Raman scattering spectroscopy is a method which is based on the laser excitation source, and it is a very very low level signal. This scattering, it shows you the scattering of your solid or liquid matter, crystal or amorphous, and it is just a fingerprint method. If you use different literature data or some libraries, you can reveal the phase composition of your sample. It is used just in hot cells, for instance, in Marcoule in France. The spent nuclear fuel samples are analyzed in the hot cell. Microscope, optical microscope, is located inside hot cell, but Raman spectroscopy and the source of laser is outside, is in your room, and they use optical wire to send the laser signal, excitation signal, and to obtain the signal from your sample. It is very useful for some uranium oxides because the difference between the uranium O2 plus X different oxidation states of uranium using X-ray diffraction is very hard. You cannot separate different uranium oxides. But using Raman spectroscopy, it is very simple. So it is very convenient. And if you have some contaminated material, you can use Raman spectroscopy using the glass vial. Inside it is your sample, and so you will be sure that no contamination go to the room, to this laboratory where Raman spectroscopy is. The next slide, please. So it is the example of using scanning electron microscopy together with along with the Raman scattering spectroscopy, microspectroscopy, to analyze different hot particles which were released around Chernobyl nuclear power plant during the accident. You can see that the composition, the phase composition, elemental, is very different of these three particles. The first is uranium O2 particle with cubic phase composition. The third is zirconia monoclinic particle, and the middle one is very complicated mixture of melted mixture of uranium O2 fuel with the zirconium border. So it is very complicated sample. The next slide, please. And the next. So X-ray methods. I know that you've got some lecture on synchrotron methods. Yeah. The day before yesterday, it is in the program. No lecture. I'm afraid that I have no time to explain all the details of synchrotron methods. They are very important for us. XANES X-ray absorption structure methods could help us to reveal the speciation of some elements, because it is unique element selective method. Even in the presence of different elements in your matrix, you can reveal the speciation of just the element of your interest. The next slide, please. But it is time. So some words about X-ray absorption spectroscopy. Spectrum has two main parts, XANES and XAFS. XANES, it is just the edge of this absorption, X-ray absorption. It is the energy is just unique for every element. You can perform your experiments so that you can analyze only the element of interest. And XANAs could help you to reveal the valence state, the oxidation state of the element. The second part is EXAFS. It is the part that can help you to find the local surrounding of the element of interest. What is on what distance and what kind of elements are around your element. So it is just very interesting tool, very important tool to find the speciation of the elements. The next slide. And I'm afraid we are to the next. Maybe it is just a special lecture for these elements. And the next. Okay, so X-ray fluorescence could be performed using synchrotron radiation or in your laboratory device. And the resolution is different, of course. There are examples of synchrotron radiation-based X-ray fluorescence to analyze bottom sediments of one of the radioactive waste storage, liquid radioactive waste storage at Mayak site. You can see the composition, elemental composition using X-ray fluorescence. You can see morphology of the particles using SEM, and synchrotron radiation-based methods could combine XRF and EXAFS XANAs, so you can find the particle of interest and reveal the speciation of elements in it. The next slide, please. X-ray tomography can show you the distribution of density. It is not just composition. Those different spots, different color, it's just only the transparency of X-ray. So it is just the density of, but we can see the sample without its destruction. You can look inside the sample. The next slide, please. And the last method is particle-induced methods. It is a group of methods which are used for analyzing the composition of matter. You have primary beam of protons. From the left, you can see this beam goes to your sample, and you have Rutherford backscattering and nuclear reactions for isotopic analysis and particle-induced X-ray emission, which can help you to analyze the composition of the waste materials. And the next slide, please. So mass spectroscopy, we have no time to speak about mass spectroscopy. And I think that it is not so important for routine analysis, only in special cases it is used. And the next slide. It is just about, and the next, and next, and the next, oh, okay. So different isotopic ratios could show you the source of your particles. They could go from different kind of explosions, for instance, if there are some nuclear testing. And the next slide, please. And the next, you can see the difference between the particles from nuclear power plant, which have a lot of time of burn up. And in the case of nuclear testing, there are very different isotopic ratio of plutonium isotopes. And the next slide. So we go to conclusion remarks at last. I would like to repeat that we use some methods like autoradiography, electron microscopy methods, X-ray techniques using synchrotron radiation, or X-ray techniques using laboratory devices, and Raman scattering. And after these kinds of non-destructive methods, we can use destructive methods, including sequential extraction techniques and experiments to choose the conditions and reagents for treatment of the waste, and so on. And the last slide. Thank you for your attention. Maybe you have some questions.
Одна направлена в зал, а вот эта направлена на вас, соответственно.
Hey, dear colleagues, let's continue. Good afternoon, dear colleagues. My name is Igor Dalyaev, and I am from RTC. It's Robotic and Technical Cybernetic Institute from St. Petersburg. We are from Ministry of Science and Education of Russian Federation also. And today I would like to make a short report about robotics also, and also about robotics in decommission of nuclear facility. So my English is not so good. That's why I will read some of my notes from the slides. And generally, first of all, what is it robots? The robots is a machine, especially the one programmed by a computer, and capable for carrying out a complex series of action automatically. It's the key word is automatically. So a robot can be guided by an external device control, like a human from human, or the control may be embedded within. Robots may be constructed to evoke human form, as we can see from the slide. But most robots are task-perform machine designed with the emphasis of stark functionality. And also we know such system like remote control system from it's at the right from the slide. They are generally not robots. In case they are not programmable by computer, only human can control them. However, the border is very blurry because if we get control inside, it will be robot also. Robot can be various purpose. It can be industrial, medical, household, military, space, underwater, and service. And generally, the most popular now is industrial and service robotics. For us, with this framework about decommissioning, also the industrial and service robotic is very important today. Modern industrial robots in factory have long become familiar. There are many kinds of robots. Generally, it's a manipulation system and a transport platform. The work of such robotics take place mainly according to software algorithm that it's rigidly tied to a technological process or technological cycle. So we can imagine how they work in auto industry. And industrial robots are designed to work in deterministic environments because every time they know in what position they should be. Sorry. But progress doesn't stand still. The sensor components of robots we were developing, they became safer for humans, and a new direction appeared. It means collaborative robotics, so they can work directly near human. Modern collaborative also it's belong to service group, and other service robots have a necessary set of sensors and developed control system to work in a non-deterministic environment. Because of developing sensory subsystem, this robot can safely interact with space and directly with human. This fact made it possible to reduce production facility several times. So the factory can get smaller. And what about decommissioning? Decommissioning of nuclear facility or nuclear facility decommission, NFD. The following main stages is, we can see following main stages. The first one is preparation for nuclear facility decommission. However, we collect facility data carry out necessary engineering and surveys and measurements, we get sampling on this stage and developing the decommissioning program. On the second stage, decontamination, the main task for this stage is to minimize a level of radiation inside buildings and structure in order to secure further handling of them. The third stage is the dismantling of equipment. At the end of this stage, fragmentation and removal of all equipment is carried out, which does not apply to building structures. And the first stage is the dismantling of building structure. So at the end of the stage, we dismantle every structure. And the fifth is reliability of the territory. The last one stage is withdraw from control. So I would like to mention that there are many different tasks on these stages, and they require a large number of technical units. We can imagine how many technical units we use in dismantling of building structure, not only in a nuclear facility decommissioning, but there also can be used here. So what's the difference between the usual demolition of structures and for decommission of nuclear facility? The difference is the generally in ionization radiation. And for this reason, it's necessary to decontaminate in stage, and also not only manual fragmentation methods are preferred, but we should use remote robotic system or other robotics for help us. Also, an important factor is a requirement on non-proliferation of radioactive contamination. Therefore, everything that is a source of radiation or contaminated should be sorted separately and sent to burial. All its natural place increased demands to equipment state and also to technical solutions like robots. Decontamination is not an easy as it may seem, because we are dealing not just with industrial equipment, but potentially with radiation objects, and it can get a significant harm to ecosystem and also to human health. That's why nuclear facility decommissioning involves the investment of large resources. The work is time-consuming, non-standard, and comprehensive approach is required to solve the existing problem. Development of new technologies is required, and nuclear facility decommissioning are characterized by several things. It's high cost, low performance, and now it's mainly manual labor or using a simplest mean of mechanization. In this situation, it's urgently necessary to develop a new methodologies and highly effective technical systems. At the preliminary stage, the analysis shows us that it's necessary to define requirement for robotic complex, including the types of work in which it is advisable to use technical equipment for them. Next one is approximate scope of work, also with the use of robotic systems. They participate of using robotic and remote robotic system, remote control system in Russia and abroad in the context of performance in decommissioned nuclear power plants and other nuclear facility. And prospecting trends in development of technologies, equipment, digital solution in the field of organization and performance in decommissioned nuclear power plants and nuclear facility. Robotic complexes are best suited for this task, which will be able to automate most tasks and minimize human participation in dangerous conditions. And in this situation, it's urgently necessary to develop new methodologies. So robotic can make in automatic mode such tasks as comprehensive engineering and radiation survey. So next slide, I will show you some robotic system for this. And the main expected results from the robotization in decommissioning are follows. timeline reduction at each stage, standardization of typical technological procedures, exclusion human factor. We can make a digital models and use them in nuclear facility decommissioning. I guess it can get us a reduction of labor costs, and generally a human radiation influence, we minimize them. Historically, our institute began working in the direction of nuclear energy at the time of liquidation, the Chernobyl accident in 1986. During that period, a significant number of robots were created, which helped fulfill the priority task of dismantling the rubble. The working condition was very difficult. That's why it wasn't important without a failure of equipment. Many robotics stay there and doesn't work enough. But this accident later served a beginning for development of specialized robotic system whose tasks are to eliminate the consequence of nuclear accidents. And our institute developed mobile platform for radiation monitoring and search of radiation sources. To perform this task assigned to the robot, it must be only autonomous, and it have a passable chassis. We can see on slide on the video. The chassis can to overcome obstacles. And as I can see from video, the obstacles sometimes are more than its clearance, as well as drive to the steps also upstairs. The robot is also equipped with a manipulation system, but not every robot. We have some robotic systems that use only for define the source of ionization radiation. To give the robot the opportunity to work autonomously, it's necessary to give a set of sensors. So it should feel the surround space. So the robot includes the sensors that allows to register ionization radiation. And all radiation reconnaissance robots carry several sensors that allow you to determine the direction to the radiation source. And robot can automatically move in this direction of the source and without human intervention. And during the movement, the robot constantly pulls the sensors to adjust the source and get with manipulation system. For comprehensively tests of such robotic system, we create a landfill. The landfill is very different. It can get different obstacles, and within the framework of this landfill, it's possible to recreate an infrastructure of the objects that we should study, or further we should do decommissioning. So we can test robotic system here, not only in at the object where is also radiation fields available. And here I would like to show some technological operations for a non-deterministic environment. We have a manipulation system. We have some technical vision system. It's a mobile technical vision system. It's stay in the end of manipulation, and state technical vision system. So for this complex, it consists from manipulation, some video cameras mounted on frame and stationary. Mobile video camera also include SSA. And we have a local docking device on the end of manipulator. The slide show an example of performing the technological operation. And this technological operation is to refuel a tank. It's just common, but not for nuclear facility decommission, but it's an example how the robots can work autonomously. The first one, after stopping the machine, the tank, the vision system determines where the filling neck located, and can manipulation system get to this docking device. If it's enough, so we get to another stage. It's also automatically, and we can manipulator moves to working position is near the filling neck, and with help of mobile video camera determines its position relative to docking point. After that, the docking and refueling is performed. At the same time, we docking the grounding couple for information cable, and immediately we mechanically closed the system. Generally, when human make them this operation, human need to dock three systems differently. It's information cable, it's other connectors, and the mechanical connectors. Also, after docking and refilling is performed at the same time, manipulation system goes to start position also automatically, like previous steps. Upon the fuel refueling in the reverse sequence also. In our experience, we just test how robotic refuel the system, and if human will control the manipulation system. And I would like to say that it's 10 times longer for human to docking. And generally, it's have many failures due docking. Also, the system can be broken because human can't feeling how it's stronger connecting. The other ways to give robotics the ability to feel is to include in manipulation system force and moment sensors. And torque sensor are integrated into each hinge of the robot. And also robotic system has a 6-component force and torque sensor at the end of manipulation. This allows the manipulation to literally touch the objects with which they interact. And also, if we control by human, we can't move robotic system with state force. And such operation like this, human can't make absolutely, because manipulation can't move. And only in automatic mode, such operation we can realize. There are sorry. Also, I would like to mention some application for remote control system. It's the experience of Rosnergoatom. They use some remote control systems like Brock to dismantling the equipment. And their conclusion that if with fragmentation large size equipment, it's allow us to increase the cutting speed by 5 times. And when we work in manual mode also, and the use of remote robotic systems when performing fragmentation of thin-walled equipment, it replaced by team of 5 people. So when we're using just a remote robotic system, we can get quicker dismantling, and we have less people in our team. But if we will use autonomous robotic system, also we can make our team more like 1-2 people, 1-2 operators. As a review that we show at the moment, there are a certain number of developments that somehow solve local decommission tasks, but there are no comprehensive solution of them. In fact, it's impossible to get a comprehensive universal solution due to the fact of large difference between the nuclear facility objects. Amount of market participant, we can mention such companies as International Research Institute of Nuclear Decommission, or IRID, OS Robotics from England, Orano, and of course Kairi from Korea. All solutions are divided into the following areas. It's dismantling or decontamination in the zone of high radiation fields. It's conducting CERS and sampling. CERS means comprehensive engineering research and sampling. The next one is dismantling and decontamination in area of general industrial work. So there are no such high radiation field inside. And the last one is inspection of structures. Some words about these companies. OS Robotics has only one solution. It's snake robot with laser dismantling in hard to research, hard to reach places. And Kairi, it's a big Korean company. For decommission, they have powerful hydraulic manipulation system. It's shown here on slide. This manipulation can work in extremely high radiation fields, and they would like to use it in dismantling the high radiation equipment like reactor and etc. And this manipulation can work also underwater. Some words about Arana. It's a company that's specialized in dismantling structures, also in the place of nuclear facility, nuclear industry, but they work only with remote control system. So they perform their work with help of humans and remote control system. And IRID is a company that's specialized in decommission tasks, and it's their general mission. So they have quite a lot of technical solution in various tasks. Purpose of this organization is to research and development technology for nuclear decommission and promoting cooperation with international and domestic organizations on nuclear decommissioning. And here I would like to show some slides from IRID. And the general tasks for now is to decommissioning of Fukushima. So they should take the corium inside the reactor and get out from nuclear facility then. As you can see on the slide, it's planned to use many pieces of equipment in this project, including cranes, as well as special manipulation system for extracting corium. At the same time, there are no ready-made solution, and everything is under development and testing. So as I know, the corium is in Fukushima also at this time. And the most sensitively elements of robotic is microprocessor technology. So it's a great problem for robotic system because the high radiation fields are danger for microprocessor, and in this case we should to remove from working area them all. And here another slide is technology elements divided into parts, also contains internal components For example, the extraction of corium from under the reactor requires a development of a manipulation, specialized tools, mean of removal and delivery, as well as mobile platform for the transfer of intermediate package for further circulation. So we can see they developed in 2019 manually manipulator system. They developed and now testing mechanical manipulation system that get into the reactor zone and get to the corium, but all electronic devices are considered in the base. And its length about 10 or 15 meters. So I would mention once time the most problem is that we should move our sensitive elements, microprocessor technique for robots outside the working area if we work in a high radiation field like inside in reactor or with extra spent fuel or with corium also. The technology elements divide into parts also contain some components, and we make our system for dismantling and fragmentation the equipment based on manipulation system. I show one slide, but it includes more robotic system just for working with equipment, with radiation equipment. So in 2020, we developed this complex. It contains two manipulation systems. One work with plasma cutting, and the complex can capture and retain the fragment structures and elements weighing no more than 100 kilograms. One manipulation can get these fragments in distance up to 4 meters. It's a length of manipulation system, hydraulic also. And the other manipulation system is electromechanical. It have about 1.5 meters length, but it's gets a plasma cutting system. So our plasma cutting can fragmentation equipment with thickness up to 85 millimeters. Due to fact of decommissioning is associated with a sharply increasing amount of radioactive waste, the task of the operational and automatic storing becomes urgent. And such system is the testing stage. Now we are working with it. And it's combined several modern technologies, the use of robotic systems, general manipulation system, also technical vision system, and advanced waste detection unit. So this sorting contains one manipulator, some amount of cameras, and cameras get to two different technical vision system. One of them is recognize the parts of equipment. The other recognize a morphology of equipment. We need it to control where we should sorting the types of it. And the selection of element is subsequent capture is carried using the vision system. The complex will work such way. So radioactive waste is going to our two manipulation system. Video cameras recognize the parts, so the manipulator can capture them, and the technical vision system recognize the morphology of it. At the output, we have opportunity to isolate the most active elements from the entire volume of radioactive waste, and therefore we are lowering the waste classification class. And for conclusion, the last slide, I would like to repeat some main tasks for robots in nuclear decommissioning. So they show on the slide, it's monitoring and inspection of emergency zones. It's radiation exploration, or CERS means comprehensive engineering and radiation survey. It's a determination of the local location of objects and the condition of technological equipment in the work area. Collection and transportation the hazardous objects to the area of their disposal. Loading and unloading and transport operation. Its robotic system can make them. Engineering works on clearing blockage and dismantling of emergency structures. Also decontamination of terrain, building and equipment, collecting and removing highly toxic and liquid and solid substance and materials from the ground and also from the building. And the last one is dismantling the structures. So the main goal for using the robotics is ensure and safety of life and health for human in this work. Thank you for your attention. Any questions? Yes, please.
Yes, I would like to ask you, for the robotics, there is always a concern regarding the reliability of the robot. Do you think the robot will be 100% reliable when you are sending it for the decontamination or decommissioning of a facility? No, what I mean to say is the reliability of a robot will always be a question. We cannot trust a robot 100%, is it not? So do you think it would be better to say, for example, send a human being instead of a robot with proper shielding?
Okay.
No, I don't think so, because we should test our robotic system. Also, we should test how many radiations then can carry out before destroyed. And if we work with a high radiation field, human can't enter there, no way. But a robotic system can move here and can make some operation, also in automatic mode. But the main problem for today is about autonomously for the robotic system in high radiation field, because the sensor should be out of the field where they work. But we have now many solutions of high radiation cameras, and we can make the main sensitive systems like a microcontroller outside the work. So there a cable and robot go about 100 meters into zone, and there he can walk. The first kind, he can walk manually. So operator in teleoperating mode, manually making some operation. The second one is autonomous operation. And as I show in some slides, there are many operations that robot make quickly and more percent than human. That's why I think the robotic system must be in decommissioning. Not everything tasks they can resolve, but I think the general task for them is a high radiation field. So if we have a low radiation field, we can do quickly by humans. Any more questions? So thank you very much.
So thank you very much. We have a next lecture from Ivan Korneev, Rosatom.
One, two, three. Oh, okay. It's working.
Ничего, давайте начинать.
Начинаем?
Да.
So let's start.
Добрый день, меня зовут Иван Корнеев.
Good afternoon. My name is Ivan Korneev.
Я представляю TWEL.
I represent TWEL.
Сегодня я расскажу про дистанционный демонтаж при выводе из эксплуатации.
Today, I will describe you the remote dismantling at decommissioning.
На примере работ по выводу из эксплуатации атомных электростанций.
As an example, I will take the dismantling of nuclear power plants.
Дистанционный демонтаж подразумевает применение дистанционно управляемой техники.
Remote dismantling assumes the usage of remote.
Дистанционно управляемой техники.
It assumes the usage of the devices under remote control.
Без участия человека, непосредственного участия человека в зоне работы.
Without active participation of humans exactly in the area of works.
Да, я здесь хочу сделать акцент, что дистанционно управляемая техника и роботы — это разные понятия немножко.
I would like to stress out that devices under remote control and robots are different things.
То есть процесс не автоматически, а все равно управляется человеком просто издалека.
The process is not automatic. It is controlled by human being in a control, but the participants of a human being is necessary.
Моя презентация состоит из 4 крупных разделов.
My presentation subdivides into 4 main units.
Это общие подходы к организации демонтажа.
Those are the basic approaches towards the dismantling during commissioning of the nuclear power plant units.
Объекты дистанционного демонтажа.
You can see objects for remote dismantling.
Методы резки.
cutting methods for remote dismantling,
технические решения.
and as you see, technical solutions for remote dismantling.
В общем, если говорить про вывод из эксплуатации,
In common, if we are talking about the decommissioning,
то все работы можно разделить условно на 4 группы.
so all the works can be subdivided into 4 groups.
Это эксплуатация систем,
Operation of systems,
которые обеспечивают безопасность.
which provides the safety of the object.
Это демонтаж,
This is dismantling itself,
дезактивация
decontamination,
и обращение с радиоактивными отходами.
and waste management.
Так, при планировании работ по выводу из эксплуатации
While we are planning the works for dismantling of nuclear power plants,
демонтаж как отдельная работа никогда не рассматривается.
dismantling itself as a separate type of work is never considered.
Демонтаж — это всегда комплекс работ,
Dismantling is always a complex of works. It's a subsequent complex of works,
включающий в себя фрагментацию и
including fragmentation and
ну
transportation
и прочие там.
and other steps.
В зависимости от объекта демонтажа,
Depending on the type of the dismantling object,
демонтажные работы при выводе из эксплуатации можно условно разделить на 6 пунктов.
so we can subdivide the dismantling works by some conditions into 6 categories.
Это демонтаж чистого и поверхностно загрязненного оборудования,
This is dismantling of the clean and that equipment that is contaminated on the surface.
фрагментация демонтированного оборудования,
The fragmentation of equipment being dismantled,
демонтаж и фрагментация металлических конструкций,
dismantling and fragmentation of metallic constructions,
демонтаж, фрагментация активированного оборудования, того оборудования, которое было в взаимодействии нейтронов.
уже деактивированного.
Да, активированного.
Активированного. The dismantling and fragmentation of the equipment activated by neutron emission, I believe.
Демонтаж строительных конструкций
Dismantling of building constructions
и снос зданий.
and actually demolition of buildings.
Общая схема демонтажных работ, она вот
The common scheme of dismantling works, you can see on that very slide.
начинается все с подготовки площадки.
So first we prepare the site, so the preparation of the site for decommissioning.
На следующем этапе производится демонтаж чистых систем, не участвующих в работе дальнейшей.
On the next stage, we remove the non-radioactive systems.
Потом демонтаж поверхностно загрязненного оборудования.
Dismantling of contaminated systems. As far as I got it, those that are, have some radioactive sources on the surface.
Отдельно выделен демонтаж активированного оборудования.
So we're separately mentioning the dismantling of activated areas.
Затем выполняется дезактивация помещений.
Next, the decontamination of the facilities is proceeded.
Да, дальше снятие из-под атомного законодательства или из-под обязательного радиационного контроля.
Exemption from atomic law and from obligatory, как вы сказали, radiation control.
И снос уже чистых зданий.
And building the premises which are already deactivated, decontaminated.
Дистанционный демонтаж можно выполнять на разных этапах здесь.
Remote dismantling can be provided on the separate stages, on different stages of the process.
Да, но мы будем сегодня говорить про демонтаж активированного оборудования, как не имеющего альтернативы.
But today we will talk about dismantling of activated areas as those that have no alternative.
Значит, на слайде представлен набор работ
So we have here the list of works
по дистанционному демонтажу.
on the remote dismantling.
Значит, любым работам предшествует подготовительный этап.
So the preliminary, the preparation stage precedes all the works.
Всегда выполняется преддемонтажное обследование.
So the observation of the objects to be dismantled is always done before the procedure.
Да, вне зависимости, было проведено комплексное обследование до этого или нет, перед демонтажом конкретного оборудования выполняется все равно обследование.
So regardless if a complex observation of the object was done or not, еще раз, вне зависимости от того, было сделано комплексное обследование,
Да, все равно перед демонтажом
before the dismantling
оборудования
of the equipment, the equipment is to be observed and examined.
Дальше оборудование, которое мы хотим демонтировать, отключается от технологических связей.
Next, the equipment which is to be dismantled is switched off of the system.
Дальше необходимо разработать
It is necessary to develop
документацию, рабочую документацию
working documentation
и обоснование безопасности.
and the basis for the safety purposes.
После получения разрешения лицензионных,
After the license is obtained,
можно приступать к
we can
выполнению
start to proceed with works, to implement the works.
Работы начинаются с подготовки и испытаний инфраструктуры, необходимой для их
The
выполнения.
work starts with the testing and preparation of the, что вы сказали? С подготовки и чего?
Инфраструктуры.
Oh, the infrastructure.
Дальше выполняются работы по демонтажу штатного места.
Это какой пункт у нас? Выше.
Вот это.
Okay, transfer of dismantling equipment to the remote fragmentation post is the next stage of the works.
Передача демонтированного оборудования на участок фрагментации.
So then it takes place the passover of remote fragmentation of dismantled equipment.
Ну, собственно, резко, фрагментация
So the fragmentation itself
и сортировка фрагментов,
and sorting out of the fragments,
контейнеризация
its placement into the containers
и передача на хранение.
and passover for storage.
Так, теперь следующий. Теперь про объекты демонтажа.
Now we are talking about the objects of dismantling.
Значит, здесь на примере блока АЭС
Now on this,
с вектором ВВР 440.
so the type of the reactor is mentioned over there on the top.
Основное активированное оборудование – это оборудование бетонной шахты.
So the main equipment of the reactor is the concrete, is the concrete vessel, I suppose.
Значит, первое – это корпус реактора.
First is the vessel itself, the reactor's vessel.
Дальше блок защитных труб,
Protecting tube unit,
корзина активной зоны.
care basket.
Так, здесь это не видно, но
It can be seen
шахта
clearly.
реактора.
Oh,
Это
шахта.
пустая шахта реактора. Это реактор.
Reactor cavity, the internal reactor cavity. Okay.
Пятое – это днище шахты.
Reactor cavity bottom.
Изоляция корпуса реактора.
The isolation of the reactor's vessel.
И водяной кольцевой бак.
An annular water tank.
Эта конструкция похожа и, в принципе, на современные реакторы ВВРовские.
So this construction is really resembles the modern units, the modern reactors that are used
В том
nowadays,
числе те, которые Россия строит
including those that Russia builds
в других странах.
in other countries.
Значит, на этом слайде представлены
On this
данные
very slide, we can see data
по характеристикам
on the characteristics
каждой единицы оборудования,
of each unit of the equipment,
в том числе интегральная.
including the integral activity.
Значит, данные получены
These data are obtained as a result of the observations,
по результатам обследования АЭС-В1 Богуницы.
the nuclear power plant Bogunitsi.
Секунду назад.
Just a moment, just back.
Ну, здесь мы можем видеть, что самая активная часть это
Here we can see that the
активные зоны,
most active part is core basket,
как самая ближняя к
because it's
центру.
the closest to the center of the contaminated area.
Значит, блок защитных труб.
So this is the protecting tube unit.
Он условно разделен на
It's subdivided
нижняя плита,
into the lower plate,
значит, межтрубное пространство, трубная
tube
зона,
zone,
верхняя плита
upper plate,
и верхние трубы, которые
and the upper tubes,
идут
in
к
fact,
крышке корпуса реактора.
which lead to the cover of the reactor, to the lid of the reactor.
Самая активная часть это
The most active part is the lower
нижняя
plate,
плита, как самая ближняя к активной зоне.
as the closest to the active zone.
По мере удаления
While-
падает, и
While we are moving from the bottom to the top, the activity drops.
и вот в эту часть БЗТ
And here in this very part,
активация практически не происходит.
activation is nearly does not penetrate.
Следующий. Значит, корзина активной зоны практически полностью активируется
The
в высокой
basket,
степени.
the basket is activated in a high degree.
И в случае демонтажа относится к высокоактивным радиоактивным отходам.
And the case of dismantling, it's referred to the high activity parts.
Так, это шахта внутрикорпусная.
So this is the cavity.
Это та конструкция, которая находится между корзиной активной зоны и корпусом реактора.
So this is very part which is between the vessel of the reactor and the basket.
Практически полностью активируется, кроме верхней обечайки.
So it's nearly fully activated, except for the upper,
Круг, рамка.
the round. Okay. Я знаю, что такое бичейка. Но в другом смысле, потом скажу.
Так, это дно шахты реактора.
This is the bottom of the reactor.
Также активируется верхняя плита.
Also, the upper lid is activated,
И активность спадает по мере удаления от
and the
нее.
activity decreases while we are moving from the top to the bottom.
Так, на слайде приведен характерный для внутрикорпусных для
On the slide, we can see the characteristics of the
для корзины активной зоны
of the active zone of the basket.
радионуклидный вектор.
So this so-called radionuclide vector.
Мы видим, что
We can see that
активность не сильно зависит от срока эксплуатации.
that activity does not depend on that very degree from the operations time.
Основной дозообразующий элемент это кобальт-60.
The main source for the activity is cobalt-60.
Основной определяющий долгоживущую радиоактивность это никель-63.
And the most long-living element that determines the activity is nickel-63.
Здесь
Here,
показаны расчетные значения мощности.
we can see the calculated figures for dose rate. Thank you.
Здесь видно, что
Here you can
человек
see
не может присутствовать при
that the human cannot be
фрагментации
present
этих
at the
конструкций.
fragmentations of these constructions.
Для того, чтобы человек мог подходить к
In order a
конструкциям,
human being to approach to these
необходимо
constructions, it is necessary
выдержкой в течение,
to keep them for,
ну, например, корзина активной зоны
for-
130 лет почти.
for example, core basket to be held for nearly 130 years for a human being can, get into interaction with it.
Значит, немножко теперь про методы резки.
Now we will talk a little bit about the methods of fragmentation.
Вообще планирование демонтажных работ начинается с определения рабочих участков.
So, in fact, the planning of the works is started of the планирование, да?
Да, планирование.
Исследование, да? On the,
Нет, планирование демонтажных работ.
so the dismantling works are planned.
Необходимо начинать с определения.
It is necessary to determine the working areas first.
Набор и состав рабочих участков зависит от той стратегии,
The number and the character of the works depends on the character of the working areas.
от стратегии, что мы будем дальше делать с
What
тем, что
is our
демонтируем.
strategy? What we will do next?
Значит, при выборе методов резки,
When we are choosing the methods of cutting,
их вообще много,
there are lots of
но
them,
не все подходят.
but not of them are suitable.
Вот на слайде представлены
So we can
базовые
hear on the
требования,
slide the basic demands
да, к
towards
методам резки,
the
которые
fragmentation
при
methods,
демонтаже дистанционно.
which can be used remotely.
Значит, обычно
Usually,
выбирают на стадии планирования, определяются, каким методом будут пользоваться и делают это.
usually on the stage of planning, it is determined which method is to be used
И делают это в рамках многофакторного анализа.
and do it while using by methods of many factors analysis.
Ну, методика простая, останавливается.
The method is quite easy. We will not stop on that.
То есть определяется
I mean that it is determined
рассматриваемых методов,
the list of the methods,
критерии сравнения,
criteria of their comparison,
выполняется качественная оценка критерия каждого.
the quality estimation of each criteria is done.
После присваивания весовых коэффициентов каждому
So
критерию
after every criteria gets its weight coefficient,
выполняется количественная оценка метода.
so the quantitative estimation of the methods is done,
Ну и принимается решение.
and
какой
decision is made
следующий.
which method is to be chosen.
Да, здесь укрупненно представлены
Here, in a bigger scale, we can see the methods which are usually used,
которые мы принимаем при
which we accept
оценке.
at estimation.
Их условно можно разделить
We
на
can subdivide them
механическую,
as mechanical cutting,
термическая резка
thermal cutting,
и гидроабразивная.
and water jet cutting.
К механической резке относятся ленточные пила,
So mechanical cutting methods are band saw,
Значит,
Circular saw, это, ну, такая циркулярка, грубо говоря, да?
дисковая.
Дисковая. Мгм.
Дисковая, гильотинный нож,
Guillotine knife
и абразивная резка.
and abrasive disc.
К термическим методам относится
Anatomical
плазменная резка,
cutting, we can refer plasma cutting,
кислородная,
oxygen cutting,
электрорезка,
electric arc cutting,
лазерная.
laser cutting,
Вот.
and some others.
Да, ну, критерии здесь,
The criteria,
они понятны.
those are understandable, those are clear.
Это возможность применения,
This is the
это
option.
минимизация образования отходов,
So we just can list them. So the minimization of waste and the possibility to make the cutting and dismantling under the water layer.
это экономичность,
This is
надежность,
reliability, efficiency, low costs.
Вообще дистанционная резка может выполняться на воздухе или
So,
под слоем.
In general, the cutting can be done either under the atmosphere, at atmospheric conditions or under the water,
В зависимости от радиоактивности фрагментируемых конструкций,
depending on the radioactivity of the constructions being dismantled
и условий проведения
and the
работ
conditions of works.
выбирают тот или иной подход.
That or another method is chosen.
Вот если говорить о
If we
опыте
talk
40-х реакторов,
About the 440s, I don't know how to translate it into
Так и
English.
есть, да?
VVR 440 VVR.
на воздухе
So in the air,
нам получилось обосновать
we can
только
base
фрагментацию корпуса
only
реактора
fragmentation of the vessel
и верхней части
and
воздухозащитных труб.
the upper part of the protective tubes.
Следующий. Здесь я коротко расскажу.
Here, in short, I will talk about the advantages and disadvantages of the different methods.
Именно для варианта, когда мы
Exactly for
режем на воздухе.
exactly for the method of cutting in the air.
К достоинствам метода можно
To the
отнести
advantages, we
безопасность.
can refer the safety.
При резке ленточной КВ практически не образуются аэрозоли.
Cutting with the band cutting method, there are no aerosols to appear,
И высокая надежность оборудования.
and the high reliability of the equipment.
Недостатком можно отнести
To the disadvantages, we can refer
необходимость
the necessity
замены режущего инструмента,
to substitute the cutting equipment frequently.
ограничения по геометрии, только простая
So
геометрия.
geometry limitations, only simply geometry works with
И
this method,
достаточно низкая скорость резки.
and relatively low speed of the cutting.
Кислородная резка.
So oxygen cutting.
Это стандартный
This is a standard.
подход.
This is a standard
Основным
approach.
достоинством
The main
является
advantage is
высокая скорость
high
резки
cutting performance
и отсутствие ограничений по толщине разрезаемого металла.
and there are no limitations for the thickness of the material being cut.
Основной недостаток
The main disadvantage,
возможность резать только углеродистой стали,
so we can only
карбонсталь.
we can cut only steel with high percentage of carbon. And as I can see, strong aerosol production.
И
Много аэрозола, да?
большое количество
Strong
аэрозолей.
aerosol production, right?
Следующий. Так, это плазменная резка.
So this is plasma cutting.
Плазменная резка аналогична кислородной.
Plasma cutting is an analog in a sense. It's similar to the oxygen cutting.
Имеет высокую скорость резки.
So it has high cutting speed.
однако имеет ограничения
However,
по
it has
толщине
limitations due to
процессуального металла.
it has limitations of the thickness of the material cut.
При использовании дистанционных
If we use it at the remote technologies,
ограничения около 80 миллиметров.
the limitation of the thickness is up to 80 millimeters.
Недостатки,
The disadvantages
недостатки это то, что
is that
аэрозольная активность высокая,
we still have high aerosol activity in this method,
ну и ограничения по толщине.
and the limitations due to the thickness of the material.
Так, это пробовали резать
So-
кислородным копьем.
It was tried to cut with the oxygen core lens. Okay,
Да.
I would translate like spear.
Значит, не обеспечивает нужного качества
It
резки,
doesn't provide the good quality of cutting.
большая аэрозольная активность.
Strong aerosol activity.
Годится только для того, чтобы
It is suitable only
какое-то отверстие и всё.
to burn a hole somewhere.
Следующее. Исходя из проделанных исследований и опыта выполнения,
Based on the experiments done and the experience
что для фрагментации
for the
на
fragmentation
воздухе
in the air,
лучше всего подойдет
the best method is
механические методы резки.
mechanical methods of cutting.
Связано это с тем, что
It's linked to the
сложно при
to
высокой
the fact that it's very
активности
difficult.
сложно обеспечить
It is difficult to provide.
точную очистку от аэрозолей.
It is difficult to provide the good purification from aerosols at the high activity.
Соответственно, чем больше активность у конструкции,
So the higher the activity of construction is,
тем сложнее
the more
обосновать
difficult
безопасность его
it
резки.
is to base the safety of its cutting.
На помощь приходит резко под водой.
So in this very case, it is very helpful to use cutting under the water.
При выводе из эксплуатации на базе
At the decommissioning,
на базе
on the basis of,
бассейна выдержки ядерного топлива,
on the basin of keeping the radioactive object pool, water pool, okay. Maybe you have the special term for this. Okay, if you know, please let me know. It is, как это сказать? Это еще раз, на основании чего?
нет, при выводе не на основании.
At
При выводе из
the-
эксплуатации
At the,
у нас есть возможность использовать
we can
бассейн
use a
выдержки.
pool, right? We can use a pool. At,
Мы можем там организовать
so we can organize the
необходимую инфраструктуру,
necessary infrastructure
где можем
where we can
внутрикорпусные устройства
do,
порезать.
we can cut the internal parts inside the vessel.
Следующее. Значит, пробовали
It was tried,
резку ленточной
cut.
пилой под слоем воды.
the band cutting under the water. In the water.
Преимущества у них остаются те же, которые на воздухе.
So the advantages are still those as in the air.
Однако есть сложность в обслуживании.
However, there are some difficulties in technical support of the equipment.
Плазменная резка под водой хорошо себя зарекомендовала.
Plasma cutting in the water has recommended it nicely.
Единственный недостаток
The only disadvantage is,
быстро загрязняется бассейн, приходится менять фильтр.
so the water pool is getting polluted very quickly. We have to substitute the water all the time.
Сейчас видео просто включим для примера.
We will just demonstrate your video as an example.
Ну вот, это на базе бассейна выдержки.
So there is about the water pool.
Создана необходимая инфраструктура, и
The necessary infrastructure is made,
ленточной пилой режет обличающий.
and with the band saw we can cut the upper
Блока
how to say, rounds, whatever.
блока защитных труб. Значит, это плазменная резка,
This is a plasma cutting,
круговая.
round plasma cutting, circle plasma cutting. I don't know this. I believe you understand me.
Защитные трубы как раз ей
The
обрезают.
protective
Ну,
tubes are cut like this from the inside.
Ну, видно,
You can see the
да,
process is followed by
выделение газа.
emission of gas.
Ну, все равно достаточно чисто.
Anyway, it's relatively clean.
Мгм. Это уже внешний резак плазменный.
So this is the external cutter,
Видно, что
plasma cutter. It is seen
не очень получается контролировать
that we
визуально
cannot visually control the zone of cutting.
Однако
However,
резко
the cutting
высокопроизводительная.
is highly productive.
Давай следующий.
Okay.
Еще один метод — это метод
Another
с
method
помощью угольного электрода.
is the cutting by usage of carbon electrode.
Не имеет альтернативы.
It has no alternatives
Подводные резки
at wet cutting
толстостенных конструкций
of the thick walls constructions
с толщиной больше 300
with a
мм
thickness that is more than 300 millimeters,
из нержавеющей стали.
made of stainless steel.
Достаточно простой
It's
метод.
relatively easy method.
Его легко реализовать,
It is easy to be realized.
не требует дорогостоящего оборудования.
It doesn't need expensive equipment.
Вот. Однако
However,
отсутствует возможность
there is no
контроля
options
процесса резки.
to visually control the process of cutting.
Нужно быть очень аккуратным, чтобы
You have to be very accurate,
обрисовку бассейна или
not to cut the vessel's external surface.
Здесь
Here,
рекомендации по применению
we can see recommendations for usage,
того или иного метода резки
this or that method of cutting
для фрагментации
for the fragmentations of each construction.
Ну, здесь практически
Here, in
всегда
practical
есть-
terms,
практически всегда есть альтернативный метод,
there is an alternative method,
кроме
And
тогда, когда нужно
except
резать
for
толстостенную
we need
конструкцию.
to cut the thick walls construction.
Здесь только угольный электрод.
Here we can use only the carbon electrode.
Сейчас, следующее. Так, это Следующее это сведенные достоинства и недостатки.
Next, we have advantages and disadvantages method to be compared on this very table.
Мы их проговорили.
We have already spoken them through.
Так, теперь
Now,
попробую как-то
I'd
показать
like to show
технические решения. по
technical
дистанционному
solutions
демонтажу.
for remote dismantling.
Здесь на слайде перечислен набор
Here,
необходимого оборудования
The necessary tools and equipment is listed
для выполнения дистанционного демонтажа
to make the remote dismantling
в общем виде.
in general.
Режущее оборудование,
Cutting equipment,
значит, фильтры,
filters,
манипуляторы,
manipulators,
и нужна обязательно защита.
and of course, we need protective containers.
И средства для сбора вторичных отходов.
And the vacuum cleaners. Yes,
Да, да.
okay.
Значит, начиная от корпуса реактора, обычно
Starting from the vessel of the reactor,
резку для отключения его технологических связей.
so it is cutting to exclude it from the technology links, technology wires.
Показан один из
Here we can
примеров.
see one of the example of mechanical.
Это машина для механической
Here is a
обрезки
machine.
корпуса реактора изнутри корпуса.
So this is a machine to cutting the internal parts of the reactor inside it.
То есть корпус реактора залит водой чуть выше активной зоны.
So the vessel of the reactor is filled with water slightly above the active zone.
Вот эта машина
This
опускается
machine
в реактор,
goes down into the reactor.
позиционируется напротив входа в патрубок.
It is positioned right the opposite of the patrobak. I don't know how to translate this word.
Нозли, да?
Nozzle. Right opposite this nozzle, right?
Раскрепляется, фиксируется.
It is fixed inside it.
И осуществляется резко фрезерование.
So, and cutting takes place.
Следующий.
Технический термин фрезерования застрелите, не переведу.
Ну, просто механическая резка. Да.
So, mechanical cutting takes place.
Значит, еще раз, выше мы эту
Once again,
картинку уже видели.
we have seen this picture above.
Она показывает, что все
It
технические
demonstrates that
решения
all the technical decisions depend on
зависит от выбранной стратегии
the
последующего возвращения.
strategy chosen for the further usage.
Здесь вот
Here,
для демонтажа реакторного оборудования возможны две стратегии.
for the equipment dismantling, we can choose one of two strategies.
То есть мы должны понять, что нам нужно
We
в
should
конце.
understand what in the end of the day,
Либо контейнеры,
we would like to have either containers
заполненные фрагментами,
filled with the fragments of the constructions.
либо
Alternatively,
корпус реактора целиком,
the reactor's vessel as whole,
который мы отправляем на
which we send
распадное хранение.
to the storage, to the long-term storage, which suppose that the inside parts will experience decay.
Да, здесь я покажу анимационную картинку.
Here I will show you an animation.
Вот корпус реактора по
So
главному разъему
The reactor's vessel,
специальным захватом, на него одевается транспортная крыша.
by a special grip, a lid is put on this vessel.
Заранее защита устанавливается.
In advance, a special protection is put into this special corridor,
И мы перемещаем
and we are moving
И защиту одеваем для того, чтобы
We are moving it.
активную зону.
We are moving it and putting protection on it in order to reflect, что экранировать?
Активную зону.
To reflect the active zone.
Ну, я сейчас пролистаю.
I will just list it briefly.
И дальше он целиком вывозится на площадку хранения.
And then, as a whole, it is transported to the place of storage.
Следующая концепция.
Next conception.
Если мы корпус реактора
If
хотим
we would like
оставить вместе с ВКУ,
to leave the vessel of the reactor
вместе с
with its internal parts.
Такой вариант тоже возможен.
This is also possible.
Давай следующий. Для этого мы используем
To do so, we use
штатный защитный контейнер для
ordinary protective container,
которым пользовались при эксплуатации
which we used before at operation,
в процессе
in the process of the service.
Да. То есть также корпус реактора устанавливается в транспортный коридор.
The same way, the reactor's vessel is established in the transportation corridor.
На него устанавливается защита.
So protection is established on it.
И внутрикорпусные устройства.
And the devices inside the vessel by means of the container
Опять собираются в корпусе, внутри корпуса.
again are collected inside the vessel.
Гидравлическим порталом корпус реактора опускается на салазки.
Еще раз, гидравлическим порталом.
Ну, да, гидравлическим порталом.
So I don't know. Okay, I'll try to translate it like this. The hydraulic portal is used to put the vessel on the rails.
И дальше грузится на платформу.
And next is loaded onto the platform. Вообще у нас 5 минут, да.
Все, отлично. Да. Фрагментация.
Fragmentation.
Если нам корпус реактора нужно порезать,
If we need to cut vessel,
это тоже возможно.
it is also possible.
Значит, мы можем его оставить либо
We can leave
в
it.
шахте реактора в бетон,
We can leave it and to cut it either in the cavity,
либо
alternatively,
либо отправить его на специально
we can send it to the
подготовленный
specially prepared, простите,
пост сухой резки.
On the special point of the dry cutting.
Здесь показана последовательность работы условно.
Here we can see the consequences of work.
Стоит горизонтальная пила.
There is a horizontal saw.
Корпус реактора
The vessel
опускается на тележку.
is put down onto the trolley.
Здесь фиксируется.
Here it is fixed.
И обрезается крупная обечайка.
And this обечайка, the round is cut. The round is cut.
Дальше корпус реактора поднимается. Оставшаяся часть.
Then the remaining part of the vessel is lifted.
Дальше уже фрагментация идет на вертикальной пиле.
And next, the fragmentation is done by means of vertical saw.
Все загружается в контейнеры.
Everything is loaded into the container.
И контейнеры едут в могильник.
And the containers are transported to the graveyard or
repository.
Repository. Okay.
Фрагментация, как мы уже говорили, выполняется на
Fragmentation is performed on specially
Специально
prepared
подготовленных
stationary
участках.
areas.
Значит, создаются зоны сухой и мокрой резки. Давайте.
So zones of dry and wet cutting are prepared.
Это пример
This is an
организации
example of
зоны
organization of zones
мокрой и
of
сухой
wet and dry cutting
на базе герметичных помещений.
on the base, I would say, on the base of hermetically isolated premises,
Освобожденных от оборудования. Оборудование, в которых было
free of equipment, free of dismantled equipment.
То есть здесь сооружается бассейн,
Here is a water pool is designed
в котором осуществляется резка.
in which the cutting is taking place.
А здесь устанавливается поворотный стол,
And here the turning table is installed
на котором осуществляется резка.
on which the cutting is performed.
Здесь шлюзы, зоны до резки, зоны характеризации.
So there are some zones of characterizations and zones on the final cutting.
Это просто фотографии
These are just the photos
возможных вариантов.
of the possible options.
Вот это поворотный стол,
Here is the turning table.
как карусельный станок. Ну, как карусель.
He's like, you know, чтоб я помнила, как будет карусель. Помню, как и есть carousel, right? It's just like that. Yeah. So it turns around. So I mean, the idea is clear. So this is a thing that turns around, right? Like a carousel. Carousel, there is a word in English, as far as I remember.
Здесь представлен
Here we can see
набор необходимого
a number of necessary tools
для зоны сухой резки.
for dry cutting.
Так, значит, это подводная резка.
Rotary table.
Следующий.
Okay, it's called rotary table.
Следующий. Значит, мы это проговорили. Здесь набор для оборудования для зоны мокрой резки.
Here is a set for wet cutting.
Здесь пример модели.
Here is an example of a model of
organization
of the wet cutting basin zone.
Вот эта часть, это
This part are filters.
достаточно важный элемент.
This is a rather important element for water needed for the pool filtration.
Также здесь поворотный стол.
Here is the rotary table
Ленточная пила может
with the band saw. So the saw can cut either in vertical or horizontal option.
Соответственно,
Respectfully,
через
through
верх идет загрузка.
the upper area, the object of cutting is loaded.
Ворота закрываются.
The gates are closed.
И работа выполняется
And the work are performed remotely by means of video cameras.
Фрагментация всегда выполняется по заранее размеченным схемам.
Is done in accordance with primitively marked schemes.
Обязательно строятся модели.
The models are obligatory done in advance.
Не только резки, но и
not on the cutting, but also
но и загрузки фрагментов в контейнеры.
But also for the loading of the fragmented details into the containers.
Следующий. Ну, здесь модель как раз представлена.
Here is a model represented.
Каждый фрагмент имеет
each fragment
заранее расчетную активность.
Has a preliminary calculated activity.
И габаритные размеры.
And their measured estimated sizes.
Каждый этот фрагмент планируется так, что он будет загружен в соответствующий контейнер.
Each fragment is planned in a way it will be loaded into the container.
Исходя из этого, мы рассчитываем количество контейнеров.
Taking this into consideration, we estimate the number of containers,
Время резки и
the time cutting, and expenses.
Здесь еще одна конструкция.
Here is another construction we were talking about previously.
Это кольцевой бак.
Here is a ring. I don't know. There is, может быть, здесь есть какой-то? Annual water tank. Okay.
Это опорная ферма для корпуса реактора. Опорная, ну не знаю.
Опорная. Basement. Here is a basement for the vessel,
Поддерживает реактор.
which actually is a basement for the reactor, which keeps it on the which keeps it and supports it in a sense.
В нее ставится реактор.
So the reactor is actually established inside of it.
У современных блоков это так называемая
Modern units,
защита.
For modern units, it's a kind of dry protection.
Сухая защита и опять вот эта опорная конструкция.
So for modern reactors is both dry protection and also, you know, the basement of the vessel.
Основная проблема демонтажа кольцевого бака.
The main problem for annual water tank dismantling,
Его невозможно демонтировать целиком.
it's impossible to dismantle it in a whole, completely.
Его диаметр очень большой.
It has a very big diameter.
Он не проходит вот в этот.
It doesn't fit this very space.
Поэтому
That is why
технология демонтажа его.
the technology of dismantling its fragments is developed.
Бак внутри заполняется бетоном.
The tank inside is filled with concrete.
И уже после этого
And after that,
фрагментируется
it is fragmentized
ленточный
by means of another type of the saw.
фрагменты дальше укладываются в контейнер и вывозятся.
The fragments are next loaded into the container and transported out of the place of works.
Следующий слайд.
Мы уже перебрали, Таник.
Все, последний слайд.
Мгм.
Здесь, значит, показана
Here we can
прекрасная
see,
стратегия, какое место в хранилище будет занимать наша.
here we can see what place the dismantled objects will take, independence of different strategies to be chosen.
Это вариант, если в корпус реактора будут загружены внутрикорпусные устройства.
This is the case where the internal parts of the reactor will be loaded inside the vessel.
Это самый быстрый
This is the
по
fastest
реализации вариант.
in the terms of realization option.
С точки зрения
From the point of view
краткосрочной
of
безопасности.
the short-term safety.
Самый безопасный вариант.
This is the safest method.
Вторая стратегия.
The second
Это
strategy,
корпус реактора отдельно,
the vessel separately.
а внутрикорпусные устройства не
The internal
фрагментированы,
devices are not fragmented.
ставятся в защитные контейнеры.
They are put into the protective container.
И самый долгий и
And the
самый
longest
большой по месту хранения
and with the highest capacity of storage method is
это вариант с фрагментацией
the
корпуса реактора
option
СКУ.
with fragmentation of the vessel.
Вот эти части корпуса
These
реактора,
parts of
они
the vessel,
чистые, они
they
не
are
подлежат
clean.
загрязнению, их можно
They are not
отдезактивировать и вставить
contaminated.
в металл.
They can be decontaminated.
Тут что можно сказать? Что
What can
самый
I-
лучший
what
контейнер
can be
для
That the best container
внутрикорпусных устройств
for the internal
сам
devices
корпус реактора.
is the vessel itself.
Если строить репозиторий,
if we consider to build a repository,
строить таким образом, чтобы была возможность
to build it in that way, to have an option
загрузки туда корпуса,
of loading there the vessel,
это сэкономит и
it
место
will
хранения,
save space
и
of
время
storage.
проведения работ.
And the time needed for works.
У меня все,
Implements.
пожалуйста, вопросы.
Thank you. Any questions?
Just a small question. What can you tell about laser cutting?
Лазерная резка
Laser cutting
активно используется.
is actively used in dismantling works.
Основная проблема
The main problem is
это дорогостоящее оборудование,
it's a high cost equipment.
большие энергетические затраты
It needs much power
и ограничения по толщине разрезаемого металла.
and limitations on the thickness of the material to be cut.
Кроме того,
Besides of
при
that,
лазерной резке необходимо обеспечить безопасность
laser cut assumes the safety
так, чтобы не прорезать
that way not to cut the basin
что достаточно
the water
стесненные
bowl.
условия для этих работ.
because these works need more space to be provided, to be implemented, to be done.
И стоит существенная задача обеспечения радиационной безопасности при лазерной резке.
And there is a very essential task of providing of safety, safety at the process of laser cut, radiation safety.
Дело в том, что при лазерной резке металл испаряется.
The metal evaporates at the process of laser
Высокая
cut
температура
because of the high temperature,
и радионуклиды, они тоже
and the
переходят.
radionuclides are transferring
Да. Причем
to the air, I suppose.
очень маленький размер аэрозолей. получается.
And the diameter of aerosol particles is very small.
Это сотые, тысячные
This is the 10th and the 100th part of millimeter
микрометры.
of micrometer. Да.
Поэтому насколько получится обеспечить защиту от аэрозолей теми фильтрами, которыми мы пользуемся.
So it is a question if the filters used at for the air filtration in this very process, will they cope or not? We have to take this into consideration.
Ну и скажу так, я участвовал в испытаниях лазерной резки.
So I personally took part in the examinations of the laser cutting.
30-киловаттным лазером мы резали.
So the laser power was 30 kilowatt.
И при толщинах свыше 300 миллиметров
And if the thickness of the material exceeded
не работает.
300 millimeters, it doesn't work.
И тяжело лазером
It is
резать
very hard
поверхность,
to cut the horizontal surfaces
потому что
by laser cutting.
не удаляется
because
реза, не удаляется
from the zone of cut we cannot remove the melted metal.
То есть когда вертикально он стекает вниз,
When we do it in a vertical way, so the metal drops down
когда ты режешь,
and it's blowed out.
когда ты режешь толстостенную конструкцию,
But when you cut the thick walls, the thick walled construction,
резко просто лазер не может прорезать, образуется,
the laser cannot cut it. The lens appears
и он просто не работает.
and it just doesn't work.
Все.
That's it. Any more questions?
Спасибо.
Thank you.
Please take your seats. Now we'll start next lecture from Mikhail Polkanov. Please, floor is yours.
Good afternoon, colleagues. My name is Mikhail Polkanov. I work at the Radon enterprise, and my experience in the branch of managing radioactive waste is 35 years. Okay, let's start. Хорошо. Enterprise Radon deals with radioactive waste more than 60 years. And after delivering the first radioactive waste at the site of Radon, about 50 years ago, Radon decided that for effective decreasing radioactive waste volume, it's necessary to have thermal technologies. Thermal processing allows to reduce the volume of incoming radioactive waste as much as possible. The main purposes of thermal treatment of radioactive waste are following: reducing radioactive waste volume, as I said earlier, transfer of radioactive waste to a chemical and physical stable state, immobilization of radioactive materials in the most reliable matrices, and providing radioactive waste compliance with the quality criteria for disposal or long-term storage of radioactive waste. Radon uses the three main thermal technologies for treatment of radioactive waste. They are: for liquid radioactive waste, we use the most suitable method is concentration with subsequent cementation of radioactive waste, but more effective method is vitrification of liquid radioactive waste in a chemically stable matrix. The second method, the conventional method of incineration of low activity radioactive waste, is used only for combustible waste. Radon has worked out some facilities for incineration of radioactive waste and furnaces of various design. And the third technology, the technology of deep thermal treatment of radioactive waste of mixed morphology using plasma heating sources. This method allows to obtain products suitable for long-term storage or for disposal. About vitrification of liquid radioactive waste. Radon has developed a technology and created the plant for vitrification of liquid radioactive waste, such as high saline solutions, pulps, saline concentrates, in induction melter of the cold crucible type to obtain chemically stable glass blocks. A cold crucible You can see it here. Has an elliptical or circular structure made of water-cooled metal tubes with a rounded bottom. The crucible is surrounded by an inductor loop. This is a loop of inductor, which is moved up or down to warm up different zones of the glass melt in the cold crucible. The past consists of liquid radioactive waste concentrate and glass forming additives is loaded through the crucible cover. The glass melt is drained through a side drain device. You can see it here. In two metal containers. The temperature of the glass in the crucible varies from 1100 to 12,500 degrees, and a garnished layer of the loaded mixture is formed on the inner walls of the crucible. Of the crucible, it prevents the contact of the glass melt with the metal body of the crucible. Следующий, пожалуйста. Radon has created a plant for vitrification of liquid radioactive waste, and you can see here the scheme of this plant, and the central device of the plant is called crucible. The plant has 3 cold crucibles. The productivity of each of them is about 25 kilogram per hour of glass of the product. And each cold crucible may work separately from others. Preliminary liquid radioactive waste is concentrated up to a saline concentration of 1,000 grams per liter, after which glass forming additives are introduced into the hot concentrate, and the resulting past is loaded into the crucible in hot form. The main advantages of the cold crucible: non-contact heating, high energy concentration and productivity, wide operating temperature range up to 1800 degrees, possibility of obtaining materials with a strictly defined composition. Among the numerous disadvantages of the cold crucible, it should be noted: large energy losses, possibility of electric breakdown of the crucible, need to select the chemical composition and conditions for obtaining the glass for each tank or batch of liquid radioactive waste. The method is very expensive for treating of low-level liquid radioactive waste, but Radon participated in some investigations on the order of the Department of Energy of USA to find the conditions of using cold crucible technology for treating liquid radioactive waste of Hanford and Los Alamos and some other sites. And we and the cycle of investigation carried out about 10 years ago proved the high suitability of the method for treatment liquid high-level radioactive waste of a number of American storage facilities. An alternative method of vitrification of liquid radioactive waste is direct heating furnace. Such furnace, already the fifth generation, have been used since 1987 in the PO Mayak for the inclusion of liquid high-level radioactive waste containing components of spent nuclear fuel in aluminum phosphate glass. More than 30,000 cubic meters of high-level radioactive waste were treated in the vitrification furnaces of the PO Mayak. More than 7,000 tons of aluminum phosphate glass containing more than 750 megacurie activity were obtained. The huge value. Nevertheless, some countries with developed nuclear energy, USA, France, and now China, prefer the technology of vitrification liquid radioactive waste in cold crucible with obtaining borosilicate glass as a matrix with higher chemical stability compared to aluminum phosphate glass. Radon Enterprise, in cooperation with a number of Russian institutes, worked on the option of replacing direct heating furnaces of PO Mayak with more maintainable facilities with melters of the cold crucible type. And now about incineration, the second process. Incineration, being relatively simple technology, makes it possible to most effectively reduce the volume of radioactive waste, which has determined the widespread of the technology around the world. Maybe this technology is the most spread in the world. Currently, the facility of radioactive waste incineration is being in operation at the site of radon, and so it was commissioned in 1983. Over the years, it has undergone several repairs and equipment replacements. The facility allows processing both solid and liquid combustible radioactive waste. The basis of the facility is two-chamber grate furnace. You can see it here. Packages of solid radioactive waste are loaded through the loading unit to the grates of the furnace. And the grate of the furnace is here. On the grate, radioactive waste are burned down in the flame of the fuel burner. After heating up the furnace, liquid combustible radioactive waste is fed through the nozzle into the combustion chamber to here is nozzle. Radon has developed a new single chamber grate furnace for radioactive waste incineration and the modernized gas purification system. One new incineration plant is operated at the Kola NPP. The assembly of another plant in the горно-химический комбинат near Krasnoyarsk in Siberia has been completed, and the process of commissioning of the plant has started. Here you can see the common view of the incineration plant, and here is the furnace. And the simple construction of one chamber furnace for incineration is here at the left part of the slide. The technology of radioactive waste incineration has following main disadvantages. High content of dioxins in flue gases from the furnace, formation of radioactive ash that requires additional conditioning operations, low coefficients of reducing the volume of radioactive waste after its conditioning, and some others. The high solubility and dusting ability of ash require the adequate measures for conditioning the incineration product. Ash from the furnace hopper is discharged into metal drums, into 100-liter metal drums. And then they are sealed with a lid and placed in a metal drum with a volume 200 liters. You can see it here. And then the three internal space of the 200 liters drum is filled with cement grout, and the drum is closed with a lid. Here you can see cement matrix. Then 200 liters of drums with ash are placed in a protective metal, or 5 drums, or reinforced concrete. Here you can see metal container, concrete container, filled with the sand or with cement grout, depending on the hazard class of radioactive waste. And this method leads to a reducing of the initial volume of radioactive waste by only 4 times. Due to high volume of protective containers and relatively little volume of real product after incineration. The metal protective containers with a capacity of 3 cubic meters are used for the packaging of low-level radioactive waste, the left one. And intermediate active radioactive waste is placed in reinforced concrete containers with a capacity of 1.5 cubic meters. It's here. And now we will speak about plasma technology for treatment of radioactive waste. Plasma technology of radioactive waste treatment is not widely spread in the world due to the relatively high cost and complexity of plasma equipment, limited resource of the refractory materials, and increased requirements for the qualification of operational personnel. I will show here 3 examples of plasma facilities operating in Europe. The first one is the Zwillac facility in Switzerland. The left one. Operating on the principle of a plasma centrifuge, into which waste is loaded through the body, left screw, The second variant is Korean, and the third variant is Spanish. The Korean and Spanish facilities load solid radioactive waste directly into the stationary melter. If here we have rotating melter, the second and the third variant have the stationary melters. And so, distinctive features of all three facilities are excessively powerful plasma torches and huge heat losses. You can see here more than 1,000 kilowatt, 500 kilowatt, 500 kilowatt, and the productivity is much less that we might receive if we could use this energy properly. At Svelak installation, it was discovered that almost all radioactive cesium loaded with waste was carried away from the melter. Therefore, the acceptance of waste containing cesium radionuclides for treatment was limited. I think that other two facilities faced the same problems. At Radon, the plasma furnace is built on a different principle, which allows to capture cesium radionuclide sublimated from the melter in the shaft furnace west layer and return them into melter. Следующее, пожалуйста. The plasma pyrolytic technology of deep thermal treating radioactive waste developed at Radon and implemented in the Pluton plant is an effective alternative to the incineration method. In 2007, a pilot industrial plant Pluton for radioactive waste plasma treatment was put into operation at Radon. The basic device or unit of this plant is shaft furnace. You can see here its construction and principle. Следующий, пожалуйста. The scheme of Pluton's plant includes a shaft furnace. Shaft furnace with units for loading radioactive waste and removing the product, slag melt, a pyrogas afterburner, and a multi-stage gas purification system. It includes the apparatus of decreasing temperature gases for neutralization of aggressive components and for filtering of radioactive particles in radioactive gases. The Pluton plant was patented not only in Russia, but also a number of foreign countries. And plasma technology allows treatment of solid radioactive waste of complex morphological composition. Следующий, пожалуйста. The product of radioactive waste plasma treatment is a slag compound with high mechanical and chemical durability. Plasma technology is applicable for solid radioactive waste accumulated earlier in storage facilities and formed during the operation and decommissioning of nuclear power plants and nuclear facilities. Unlike the most common grade incineration furnaces, the shaft furnace of the Pluton plant treats bulk and powder materials, ion exchange resin, silts and slurries, thermoplastic polymers, waste with high humidity. Следующий. The nominal capacity of the Pluton plant ranges from 150 to 250 kilogram per hour. The operating temperature in the shaft furnace smelter varies from 13 to 1400 degrees, depending on the viscosity of the slag melt, and is provided by two plasma torches. According to the terms of the license, radioactive waste of very low and low activity levels are treated at the plasma facility Pluton. Следующий. The throughput of the plasma plant depends on the morphology, ash contact, humidity, and a number of other solid radioactive waste indicators. Restrictions are imposed on the content of refractory components, ferrous metals, and materials containing aggressive component, chlorine, sulfur, phosphorus, in the treated waste, which create additional corrosion impact on the gas purification system. Direct current electric arc plasma torches developed at Radon Enterprise are used as heating sources for the melter of the shaft furnace and the pyrogas afterburner. Plasma torches are 2.5 times more efficient than fuel burners in terms of heat transfer and contribute 3 or 4 times smaller volumes of the flue gas on the plant compared to fuel burners. Следующий. The plasma torches used provide heating, melting, and homogenization of the slag melt, which is drained into metal receiving container. See, you can see the metal container with freshly drained melted slag melt. Следующий. Receiving containers with cooled slag are placed into metal or concrete protective containers, as I said earlier, depending on the radioactive waste hazard class. The plasma technology of radioactive waste treatment provides maximum volume reduction coefficients. For certain types of radioactive waste, the most hard for treatment, for example, pressed in drums, the volume can be reduced by 10 times. The shaft furnace works optimally in the range of the content of non-combustible materials in solid radioactive waste, such as concrete, cement, soil, thermal insulation, etc., from 10 to 40%. And the content of non-combustible component is beyond the specified limits. The shaft furnace converts into an incineration furnace, or the waste reduction coefficient falls below 5. You can hear this diagram. Следующее. Thus, the plasma technology has a number of significant advantages over traditional radioactive waste incineration process. Due to the reduction of radioactive waste volume by 10 times, the plasma method reduces the need for certified container and saves the volume of radioactive waste. Storages eliminate a number of waste condition operations. Следующее. The volume of flue gases of the Pluton plant in specific indicators is about 2 times lower than the volume of emissions of radioactive waste incineration plant. And the formation of highly toxic components is less by 2 or by 4 times for plasma comparatively to incineration. And one more thing. The plasma process reduces the emission of carbon dioxide 4 times for each kilogram of treated waste compared to the process of incineration of radioactive waste. You can see it here. Следующий, пожалуйста. The slag obtained by the plasma method contains more refractory components and less alkali metals compared to borosilicate glass. So slag melt viscosity is significantly higher than the glass melt viscosity, and a higher temperature is required to drain the slag melt. You can see it here. Следующий. Since 2017, Novovoronezh NPP operates the plant for radioactive waste plasma treatment. The prototype of which was the Pluton plant. The plant has technical characteristics similar to the Pluton plant. And the annual capacity of the complex is 1,500 cubic meters of solid radioactive waste formed during the decommission of units 1 and 2 of the Novovoronezh NPP. И следующее. I have presented 3 types of high temperature technologies for radioactive waste treatment. The technology of liquid radioactive waste vitrification in the induction melting device called crucible is currently actively developing in the USA, France, and China. The incineration process remains the most common technology of thermal conversion of radioactive waste, and plasma technology allows for reliable and economical disposal of radioactive waste now without postponing the solution of the problem for diseases, for decades. Oh, sorry. Thank you very much.
Maybe some questions? Dear colleagues? No? Okay, from online also no. Thank you very much, Mikhail. Thank you.
Thank you very much.
Let's move to the next presentation. Yeah, Sergey. Okay. This one.
This is plasma torch can work. And here you can see the drainage of slag melt. Thank you very much.
Thank you.
Good day, everyone. I'm Sergey Somin from Twell Company. This is Rosatom subsidy entity. Probably you know that Twell Company mostly is a nuclear fuel supplier. Each 6 nuclear reactors in the world are working used of our fuel. But I suppose that someone knows that Twell has its own combines, which provide the services related with uranium enrichment and fuel assemblies production. So we have our own radiochemical plants with huge amounts of radioactive metal waste as well. And now I'm working in Twell Company, and previously I was working in Kurchatov Institute, and my zone of responsibility now and at last was radioactive waste management and decommissioning activities. And now I want to present you a briefly report considering radioactive metal waste treatment. My report will be will contain mostly examples of our own Rosatom real experience, then theory. However, this slide is the first and last in my presentation, contains a little bit of theory. Probably you know that there are 2 principal different types of radioactive metal waste, which could be generated on any kinds of nuclear sites. First type, at the left side, this is the radioactive metal, contains only the surface radioactive contamination. Surface contamination mostly could be presented by corrosion products or sediments, paints, dust contains nuclides. And the main goal of decontamination of such kind of metal is to remove these surface substances with nuclides. And the second type of radioactive metal is the metal with inducted radioactivity as effect of neutron influence. And the main difference from the first type is that the metal material becomes to generate the radioactivity by itself. For example, such kind of irradiated metal and with the inducted radioactivity could be the metal fragments from the reactor pressure vessel, from the loops and channels of the reactor vessel. Next slide. Yeah, that the theory is over. So the question is what we could do and how we should manage with radioactive metal waste. This slide contains the diagram explain the most usable approach in the metal waste treatment, which we commonly use in Rosatom entities on sites of our nuclear entities. Metal waste could be generated as a result of nuclear objects maintenance, repairing activities, and decommissioning activities as well. As for other types of waste, the first stage is radioactive control, the survey of the level of radioactivity, specific activity, surface activity, nuclides composition, and so on. And as the other types, after we provide the radioactive metal control, we could decide what kind of metal we have and could transfer it into the free release metal, hopefully for the following stage of decontamination works. And if we have irradiated inducted radioactive metal, the only way is the melting. I will say about it a little bit later, or direct storage or disposal. Based on the data of radioactive control, we select the optimal decontamination methods. Basically, there are two principal general decontamination techniques: is a liquid decontamination and dry mechanical decontamination. Taking into account the different technical and physical and chemical aspects of contamination and economical issues, we select the optimal technology and method of decontamination. But I pay your attention at this slide, at the end, in the bottom of this slide, you could see that every method of decontamination provides the secondary radioactive waste. Next slide, please. The most common technology for metal waste decontamination is a liquid chemical decontamination, and the core of this technology is a bath with alkaline or acid solutions inside. You could see at the left upper figure the huge bath which contain the metal cage with contaminated metal fragments. So the contaminated metal fragments put inside the metal cage and removed or moved forward to the bench and put inside the chemical solutions. So high temperature and aggressive chemical solutions provide the etching of metal surface and dissolve metal surface contamination. Sometimes to intensify the process of etching, we use high temperature of chemical solution, and we use the special technology called ultrasonic decontamination. At the right upper figure, you could see the example of equipment called chemical ultrasonic decontamination. And at the left bottom figure, you could see the structure of common liquid decontamination facility. It contains more often 3 baths. First of all, with chemical aggressive solutions to dissolve or each metal surface. The second one bath contain probably dissolved water to wash the aggressive solutions from the surface of metal. And this last bath is some kind of thermal bath for drying of metal. Also, this facility contains 2 or more tanks for neutralization and tanks for containing accumulation of the chemical solutions. Next slide. As I said earlier, sometimes we use ultrasonic for decontamination process intensification. Thus, bath walls are equipped with hundreds of ultrasonic converters, which could generate ultrasonic waves. So jointly with chemical decontamination, we provide the physical influence on contaminated surface. As a result, the decontamination process duration could be reduced in times. On the bottom figures, you could see at the left side, the fragments of pipes with corrosion and nuclides contamination. At the right side, the results of chemical and ultrasonic decontamination. Next slide. In this slide, you could see images of metal surface before and after decontamination process and comparison of using chemical decontamination without and with ultrasonic. You could note that ultrasonic allowed to reduce decontamination duration in time in 37 times, approximately. Okay, however, our experience demonstrates that ultrasonic allows to achieve the best results in case of typical shapes of metal fragments. Ultrasonic piezoelectric elements arrangement have to repeat the shape of metal fragments. In other words, ultrasonic piezoelectric elements have to be placed as close to the contaminated surface of metal as possible for better results. Next slide. A few words about advantages and disadvantages of liquid chemical decontamination process. Surely the main advantage is a low power consumption, high decontamination coefficient as well, high coefficient or decontamination rate, possibility to provide decontamination of internal metal surfaces without necessity of its previously fragmentation and opening. However, the main disadvantage of this technology is a huge amount of secondary liquid waste with difficult chemical composition. And this secondary waste, liquid waste, should be also treated and solidified by the end. So you should calculate possible benefits or losses of this type of decontamination process, taking into account the necessity of secondary liquid waste treatment as well. And sometimes the economics of this decontamination technology demonstrates not so attractive results. Next slide. Move forward to the dry decontamination technologies. In this slide, you could see common mechanical decontamination techniques called shot blasting decontamination. There are 2 main groups of blasting decontamination. First of all, it's automized shot blasting chambers. You could see an examples of such kind of equipment and facility at the left upper and left bottom figures. And the second option or second type is a manual blasting decontamination. You could see the worker with a shot blaster inside the closed chamber. For automated shot blasting, we use industrial chambers with different size of internal surfaces, internal space. Previously, fragmented metal fragments placed inside the blasting chamber with hook. Doors of chamber are closed, and drops moved by compressed air to the contaminated metal surface, heat with it, and remove the contamination. As alternative, there is a second option of manual blasting technique. In this case, worker move the blaster and direct the drops flow to the contamination metal surface. What about drops? Drops are made from metal, sand, or even the ice. Metal drops could be recycled several times, but all sand drops became to be a secondary radioactive waste because the spent sand drops are mixed with removed radioactive contamination. Next slide, please. As a main advantage of this technology is that the volume of secondary waste is lower than in case of liquid decontamination technology, and there is no problem to collect all spent drops and put it in storage container as a simple solid radioactive waste. But this technology has one important disadvantage. To provide the decontamination, you should cut all metal fragments to open its internal surfaces. I mean to open the internal surfaces of pipes, pumps, tanks, and so on. For example, to have a chance for influence of drops and heating the drops of these internal surfaces. And often these cutting technologies, cutting procedures is also manually. So the worker have to cut the contaminated pipe or contaminated tank manually before the decontamination. So if you have a deal with highly contaminated metal equipment, pipes, pumps, and so on, I suppose that nobody wants to cut it manually. Next slide. Another type of dry decontamination is a high temperature decontamination within laser decontamination. I'm sure that all of you understand and imagine how it works, but nevertheless, I note a few words about it. The laser beam heats up the contamination surface of metal. All surface contamination turns into the material plasma and removed. Yes, the laser decontamination is quite easy to use. Simple technology allows providing the decontamination of different surface shapes. However, as I said, the plasma is generated. It means that the plasma contains the gas aerosols and vapor phase are generated. So gas aerosols contain ultrafine radioactive dust particles. Vapor phase contains even the sublimated nuclides. So it's really challengeable to collect and treat contaminated gases, radioactive gases, after laser decontamination. This is a main disadvantage of this technology. Next slide. Okay, well, time for melting decontamination technology. Many companies in the world are used this technology. Probably you know Sweden company Statsvik, French company DF Saklife, and so on. In Russia, we have two companies which provide the same services, and one of them our Angars combine. At the core of this technology is the metal furnace. It's well known that the different nuclides have a different chemical and physical properties. It means that we could try to separate nuclides within special additives. During the melting process, we add special chemical reagents which allow us to collect some parts of nuclides in a slag on a melting upper surface. In a table at the right side, you could see that the different nuclides have you could see that how the most part of nuclides are distributed between melt, slag, and off-gas system. The most part of concentration, for example, of uranium nuclides and strontium nuclides are transferred into the slag and could be easily separated from the other metal body. At the same time, most part of cobalt is continued to be in the melt. But I pay your attention to the cesium. The temperature of cesium sublimation is between 4 and 6 centigrades. Thus, during the melting process, when the temperature inside are higher than 1000 degrees, cesium becomes to sublimate. Thus, half part of all cesium, and even more sometimes, is transferred to the off-gas cleaning system. And as in case of laser, also it's quite challengeable to treat such contaminated gases. Next slide. In this slide, I paint the scheme of melting decontamination. So if we have a surface radioactive contamination concentration higher, that it's approved by limits. we provide the decontamination. But for example, in case of inducted radioactivity, which I mentioned in the second slide of this presentation, we have an activated surface, which is radioactive by itself. Then we provide the melting with special additives and separate most part of nuclides to the slag. Finally, we have only 5 or 10% of input mass as a radioactive slag and more than 90% of clean metal. All surface inducted activity was transferred into the slag or mixed through the whole metal body. Thus, we have a clean metal. We have a clean metal as the surface radioactivity now is satisfy the criteria for pre-release metal. The main advantage of melting decontamination technology is a high decontamination factor and availability to treat even inducted radioactive metal. However, this is power-intensive technology, and special off-gas cleaning system is also required. And finally, you have to develop a small melting plant on your nuclear site. Next slide. Few words about very interesting decontamination technology called form and film decontamination technique. There are quite express decontamination methods which allow us to provide on-site decontamination of equipment surface right on its place. You just should spray special compound or apply it with a brush on a metal surface, wait for a while and remove the dried film manually, as a man on the right image. Most part of surface contamination will be collected, stacked with film, and removed from the metal surface. You could provide this operation several times to reach the better decontamination factor. We often use this technology when we need to provide on-site decontamination of any kinds of equipment, internal surfaces of hot cells, hot chambers, without its decontamination, without its mechanical decontamination. Finally, we collect removed contaminated film as a radioactive waste. However, such kind of radioactive waste will contain organic components and surface active agents, and it's quite challengeable to prove for our regulatory bodies that this is the final form of or conditioned form of radioactive waste, and we do not provide, we haven't provided any other further technologies to treat these film and forms. And last slide, hopefully. In this slide, you could see another type of decontamination technology called electrochemical surface decontamination. Sometimes we face with difficult contamination, as plutonium. Especially, this is the often case in hot chambers. You know that plutonium has a quite high adhesion properties, and you never remove it with foam and films, for example. But if you need to provide the decontamination of the surface of hot cell with plutonium, you could use the electrochemical surface decontamination. Special design suction unit is fixed on a contamination metal surface. Under its cover, there is a process of etching. Dissolved contamination is removed with suction unit, which you could see on this slide. And finally, we have a clean surface. This is a very efficient technique, but with low capacity of decontamination process and secondary liquid waste as well. So you see how many decontamination technologies could be used. However, in each case, each time you should provide the comparison of benefits and losses, calculate the economic effects, taking into account many aspects of as a power consumption, amount of secondary radioactive waste, the needs for a complex of gas cleaning system, and surely decontamination coefficient which could be achieved. Many thanks for your attention. Your questions, please. We have a question from the chat. What's the energy and source of laser used for decontamination? I try to answer it. Mostly we use the laser with power up to the 8 kilowatts. Considering the sources of laser, we use the wide range, different types of laser sources. This is not so important issue for laser decontamination.
Vladimir, do you hear us?
Yes, hello.
Yeah, hi.
Good evening.
So, can we start from?
Yes, just a
Okay.
moment.
Okay.
One moment.
Yeah.
Yep.
Yeah, perfect. Thank you.
Just
Yeah, let's start. So, floor is yours.
yeah, thank you. So, good evening once more time, and today we'll speak about radiation safety. As far as it is quite important to provide the safe work conditions for personnel. But what when we speak about the radiation safety, we should understand how different ionizing radiation interact with matter, how to protect this different against these different types of ionizing radiation, and how to measure them. So, at first, I would like to start with just short introduction to the action of ionizing radiation. So the ionizing radiation can be really harmful. We all know about the, let's say, direct action of ionizing radiation when the organs of the human body are irradiated, they are damaged, and it can be seen as a damage of skin or damage of eyes, or if we are speaking about the prolonged action of ionizing radiation, it can be cancer or other diseases. But if we will see how it started the work with radioactive materials 100 years ago, the people were not afraid of action of ionizing radiation. The properties of the new elements like radium or polonium, they thought as a, let's say, miracle because they irradiate some unknown rays, and the properties of this rays were not magic, of course, but they were not understandable at that time. And these elements like radium, polonium, thorium, and uranium, they thought to be useful and healthy elements, let's say, and they were added to many kind of everyday products like chocolate or toothpaste, or the salt for baths, or even water. And yeah, of course, it was not healthy as we know now, but at that time, people used these elements in many applications. And the first documented victims, let's say, of ionizing radiation were the people who worked with radioactive materials and ionizing radiation, like Marie Skłodowska-Curie, so the discoverer of the radium and polonium, and twice Nobel laureate. So she died of aplastic anemia, and her body contained quite a lot of radionuclides. Another victim is Clarence Daly, who was the assistant of Edison when he worked with the X-ray techniques, and he had this hand amputation, and he also died of aplastic anemia. And another man listed here, Eben McBurney Byers, he was not a scientist, but he was a rich man who was rich enough to buy quite a lot of the water solution with the radium salt, so they were quite expensive. But he was rich enough, and he drank approximately 1,400 bottles of this Radiator water. And the result was the necrosis of the jaw bones and radiation anemia, so he died quite early. Another interesting example of how people didn't care about the ionizing radiation is so-called pedoscopes. So it is apparatus when you can see your foot inside the shoe. So these pedoscopes were used quite frequently in the shoe shops. You can see that it is quite convenient to see how the shoe fit to your foot, and thus people use this in the shops. But as far as quite intensive X-rays were used, here you can see this I would say optical system. When people just look on the phosphorescent screen, so the screen was phosphorescent just by the action of X-ray. So you can imagine what the intensity of X-ray were used at that time. And of course, people noticed that people who worked in this shoe shops, they started to have quite frequently also aplastic anemia and other cancer diseases, and it was quite that these pedoscopes caused this disease. But that is interesting that the last pedoscopes were still in some shops until the late 1970s. So in USA, for example. So at that time, people already knew about the negative action of ionizing radiation, but still these techniques were used. Another quite famous case was the radium girl, so-called radium girls. So it was an enterprise where girls, mainly girls, they put the paint with the radium salts on the watches, on the compasses, on these arrows and the numbers of these compasses and watches, and they used just the paint with radium salts, and they used the brush to this paint on the compasses, and of course they make the edge of the brushes thin by putting them in their mouths, and thus they consumed quite a lot of radium, and there were dozens of cases of also cancer of jaw bones, cases of anemia, and many of these radium girls was harmed by action of ionizing radiation from radium. But today we know that radium, specifically isotope of radium-223, can be used as a pharmacy, as a medicine for treatment of their bone because radium is chemical animal, and the radium goes to the bones, and radiation from radium kills the cancer cells. So you can see how the application of radium evolved from the very harmful, let's say, action to the very useful action. And the reasons of why people at that time didn't care about the negative actions of ionizing radiation is that, of course, it was a lack of knowledge about this action of ionizing radiation. It was quite new phenomenon, and there was quite a little knowledge about action of ionizing radiation. And of course, they were quite small amount of radioactive materials, and so quite not enough statistics, let's say, about these effects. Even when people started to understand how hazardous the ionizing radiation can be, they started to apply and to develop safety standards. The first safety standards arose in 20s, so let's say 100 years ago in the UK, but it was just the beginning. It was just a few rules how to handle and what can be the safe management of the radioactive materials. And again, as far as not a lot of people knew about the safety standards from the abroad, and they didn't understand again. So due to the lack of the knowledge, they used the radioactive materials in not a proper way. But even if they knew about the safety standards, if they knew the rules, very often they broke the rules, and thus they had quite high doses of ionizing radiation. And sometimes probably know about the accidents, then people stole the sources of ionizing radiation, and they didn't know about what is it, what they stole. They use the sources of ionizing radiation in not in a proper way. You maybe know about the case in Brazil or maybe in other countries. Then the sources, medical sources of ionizing radiation, like cobalt-60 or cesium-137, they were stolen or just taken from the old and abandoned medical facilities, and then they come to the just common people, citizens, and these citizens they broke these ampoules and see some powder or whatever, if we are talking about the cesium salt, for example, and they didn't know what is it. But due to these actions, quite a lot of territories become contaminated, and people were harmed, and so it was quite a lot of negative consequences of such actions. But today we know how different types of ionizing radiation interact with matter, with biological objects. We have quite a lot of safety standards, and today the misuse of all these sources of ionizing radiation is minimal. So to understand how to protect the radiation safety, we should understand how different ionizing radiation interacts with matter. You know about the alpha, beta, gamma, and neutron radiation, and alpha and beta particles. They have very short ranges in the solid materials. Thus, if the sources of alpha or beta radiation located outside, they are practically harmless. So there is no negative, almost no negative effects from them. If it is pure alpha or beta emitters, because you can easily stop them by just the thin shielding. For alpha particles, it can be just air. For beta particles, it can be some small amount of water or clothes or whatever. So these materials, they're not so harmful. But if alpha or beta emitters enter the body, that means that they give the whole their energy to the body. That means that all the energy produced by alpha and beta emitters will be accumulated by the body. And in this case, alpha and beta emitters are the most harmful radionuclides. For the X-ray or gamma sources or neutron sources, it is another story, because they have long penetrating range. So that means that if we have gamma or X-ray source outside of the body, they can reach us. They can reach out the body and can be hazardous for our organisms, for our bodies. What are the main mechanisms when ionizing radiation come to the matter or come to the body? So in principle, we can distinguish ionizing radiation by directly ionizing or indirectly ionizing. So directly ionizing radiation, it is radiation that brings to the material the charge. So that's why it is directly bringing the charge. That means it is directly ionizing radiation. And it is electrons, positrons, or heavy charged particles like alpha particles, or if you have some accelerators, it can be protons, or it can be even heavier nuclei. Indirectly ionizing radiation don't have charge. The charge produces by the action of this indirectly ionizing radiation. It is X-rays, gamma rays, and neutrons. Due to the action of indirectly ionizing radiation and directly ionizing radiation, a lot of new ion pairs produced. Many molecules are excited. They irradiate this energy of excitement by either visible light or by thermal waves or whatever. And we can measure either the produced current or the heat that is produced, and we can measure them, these effects of the ionizing radiation interaction, and we can use these effects, either current, electron current, electric current, or the produced heat, to understand how much energy is absorbed in the material, and it is the basis for the dosimeters to understand what the energy is absorbed by the material. And we can recalculate it to the doses that we can use to estimate the biological effects. So I told you that in different materials, either indirectly or directly ionizing radiation can produce ion pairs or excited molecules. But what is the result of such actions in living organisms? So in living organisms, we have more than half of our organism is the water. So the main molecules that are that's destroyed or modified by the action of ionizing radiation is the water molecules. And water molecules produce radicals or active species like oxygen radicals or peroxo radicals or other active species. And these active species can interact further with biomolecules like DNA or with proteins or with ferments and others. So these chemical reactions will change the properties of biomolecules that will lead further in the change of the processes in the living cells. And it can result either in death or mutation, so it is bad action. When we say that ionizing radiation produce radicals or other active species, and then these radicals and active species react with biomolecules, we are speaking about indirect action of ionizing radiation. But ionizing radiation can directly react with the biomolecules like DNA. And under action of ionizing radiation, DNA can be destroyed, and the result will be also either death or mutation. So it is indirect action and direct action of ionizing radiation. And when we speak about radiation protection of living organisms, mainly human organisms, we say that radiation protection is based on the three pillars of radiation protection. So it's justification, LR principle, or as low, so LR means as low as reasonably achievable, and the dose limits. So what does mean justification? It means that if we can reach our goal, for example, in some scientific research or whatever, without using radioactive materials, then we should not use the radioactive materials. But if we cannot reach our goal without using these radionuclides or radioactive material, then we must use these radionuclides. So this justification means that we should really understand: do we need really these radionuclides or ionizing radiation or not? If not, don't use it. If we must use radionuclides or ionizing radiation, we should use as low activity, as low radioactivity as it's reasonably achievable. What means reasonably achievable? That means that we should reach our goal by using the radioactive materials, but the activity should be small, but not as small as zero, let's say, yeah. So the activity should be high enough that we can see the effect of these radionuclides in our research or whatever. So the activity of radionuclides or the intensity of ionizing radiation should be high enough to see the positive effects, the effects that we would like to see. Because if the intensity will be not this high and our research work, for example, will be useless, but we used radioactive materials, so it is really strange. So we used radioactive materials, we had some additional doses, but we didn't see the effect. So it was absolutely useless experiment, and we just received some additional risks for our health. So that means that we should use as low activity as it can be used, but we should see some effects in on our research or whatever, or on our organ. For example, if we are using radiopharmaceuticals, we should see the positive effect of the action of these radionuclides. And if we use ionizing radiation, radionuclides, we should confirm that the doses that personnel or personnel accumulates, these doses are below the limits that are provided or developed by the authorities. So those limits, there are of course recommendations from IAEA, but every country set their own limits and their own levels for these doses. And if we are working in the range below these dose limits, then we can say that we are in a safe work conditions and everything is okay. But if the doses are above these dose limits, then we should take some actions, first to decrease these doses, and also actions to provide the healthcare for this personnel who got these high doses of radiation. And there are quite a lot of different dosimetric quantities. So how to estimate these doses that personnel got? We have different quantities of for dosimetry. It is physical quantities, but for us, the most important, let's say, quantities are protection quantities. It is equivalent dose, effective dose, but we cannot measure these protection quantities directly because we cannot put the dosimeter in the human body. That's why all the protection quantities, they are calculated either from physical quantities or operational quantities that we can get from the measured quantities. So it's measured quantities is just the response of our dosimeter. So let's start with the physical quantities. So it's a fundamental quantities in dosimetry, and first is absorbed dose. So absorbed dose, just a simple definition, is the energy absorbed in the object divided by the mass of this object. So the unit of the absorbed dose is gray, so just 1 joule per kilo. And another physical quantity that can be maybe difficult to be understood, it is kerma. So it is kinetic energy released per unit mass. And what is the kinetic energy? So the kinetic energy in this case, it is the energy, kinetic energy, of the charged particles that are produced by indirectly ionizing radiation. So this term, kerma, we used only for indirectly ionizing radiation, for gamma radiation, for X-ray radiation. And it is, again, the energy of the produced charged particles. The unit for kerma is the same as for absorbed dose. It is it is gray, and 1 gray is equal again to 1 joule per kilo. There is one old quantity that is that you can still meet in many books and even in practice. It is radiation exposure dose, and by definition, it is a total charge. Total charge that is just a charge of the charged particles produced also by indirectly ionizing radiation, specifically by X-rays. So this total charge generated in air divided by mass of the air. So this radiation exposure quantity was one of the first quantity that was used to estimate the energy absorbed in the materials, because it was quite easy to measure the charge that is produced in the air. So just because of the experimental technique, this radiation exposure quantity was used. And the unit of this quantity in standard system, it is coulomb per kilo, but very often you can see the Röntgen unit of this radiation exposure quantity. Today, they are not used in dosimetry, but still many dosimeters they are calibrated in these Röntgen units. So, what are the protection quantities that we can obtain from the physical quantities? First, it is absorbed dose in an organ or tissue. So, even from the name of this unit, I think it's quite understandable that it is just absorbed dose, but it is a specific dose absorbed in a specific organ. So T here means tissue, or organ. So the unit is the same, gray, but as we see even from the beginning of the lecture, different types of ionizing radiation, they have different effects on the matter. Alpha, beta particles, gamma rays, they all interact with matter with different mechanisms. And so the results of their action are different. And to take into account this difference of different type of ionizing radiation, there is equivalent dose. Equivalent dose, it is absorbed dose in tissue or organ multiplied by the specific weighing factor for this type of radiation. So this weighing factor is equal to 1 for gamma rays or X-rays. It is equal to 1 for electrons or muons of any energy. That means that it is quite simple conversion from the absorbed dose to the equivalent dose for this type of radiation. But for alpha particles, you can see that this weighing factor is equal to 20. That means that for living organisms, the alpha particles are 20 times more hazardous, more dangerous than electrons or gamma rays. And the unit for equivalent dose is Sievert, named after Rolf Maximilian Sievert. Again, equivalent dose uses the difference between different types of radiation. So the type of radiation is important for this dose. The next dose is the effective dose. Here, we use the weighing factor for radiation, but for the tissue that is irradiated. It is important when we have some irradiation of not of the whole body, but for example, hands or eyes or I don't know, chest or other organs, and we use effective dose to calculate these risks for the organ. This weighing factor, they are not absolute. So for equivalent dose, this weighing factor, they have absolute value. So this 1 or 20 or 2.5, it is absolute values. But for weighing factor for tissues, they are not absolute, but they are specific values. So in total, the sum of these weighing factors will be equal to 1, because it is the whole body. So we summarize all organs of our body, and we get the total, the whole body. So the sum of weighing factor is equal to 1. So these weighing factors, they just show you how more sensitive one organ in comparison with another. So it is just a schematic representation of these different organs with their weighing factor. And now, what are the dose limits? So now we know about different doses and what are the dose limits. And for people who work with radioactive materials with ionizing radiation, the dose limit, annual dose limit, is equal to 20 millisievert per year, but it is average in 5 years. So in one single year, it can be as high as 50, but not more. But in average for 5 years, it should be not higher than 20 millisievert for one person. For another organs like hands and feet and skin, the dose limit can be higher, either to 500 or 300, depending on the country. And you see that for public, these doses are much lower. It is 10, 20 times lower than for the occupational workers. Why it is so? It is not because occupational workers, they are Superman, and they can withstand higher radiation doses than public, than just normal people. But it is because radiation workers, they have medical tests every year, so it will be much. So if there is some negative effects of the work conditions, it can be seen much faster than for the public, where not all, let's say not all the people have this medical test every year. Yeah. So for public, in general, we have this much lower doses than for radiation workers. Yeah. So to see what is the safe conditions for workers, it is about 12 microsievert per hour. But it is when we work 6 hours per day, and in total we work 1,700 hours per year. So in Russian Federation, we have these standards for radiation workers. Of course, usually we work more hours, but in standard it is this number of hours. So, and in principle, this radiation dose rate, 12 microsievert per hour, can be safe. If you will look on the second floor of our division, there is watches that show also the dose rate at the moment, and normally it is 0.1 microsievert per hour. So it is 120 times lower dose rate in normal condition than it is allowed for radiation works. So operational quantities, what it is. So there is an ambient dose equivalent and personal dose equivalent. What is it? So actually, it is quite simple to understand. In this case, to calculate the ambient dose equivalent, the special tissue equivalent phantom is used. Again, this phantom, it is a physical object made of plastic, and this plastic is equal to the biological tissue with this number of element content: oxygen, hydrogen, carbon, and nitrogen, with average effective charge 6.5 and density of 1 gram per cubic centimeter. And the radius of this phantom is around 30 centimeter. So let's say that human body is a sphere with the radius of 30 centimeter. But in this physical object, you can put, just physically put the dosimeter inside this phantom. Or you can use different models, mathematical models, to calculate the dose rate in this phantom. And you put the dosimeter on the certain distance inside the phantom, and you measure the dose or dose rate inside the phantom, inside this physical object. And from this value, you obtain this ambient dose equivalent that you can use to calculate further the equivalent dose. So why we should, or why we can use this phantom? Again, the material is equal to biological tissue. That means that the doses that are obtained by this object is equal to the doses that our body will obtain. This phantom is used in specific, so we model or we create the same radiation conditions, the same as the conditions when personnel will work. And we measure just experimentally the doses inside the phantom. So we can predict what equivalent doses people can get under this radiation conditions. For personal doses, another phantom is used. So again, it is biological tissue equivalent material, but in this case, it's just a slab. So it's not a sphere, but it is a slab. And the dosimeter can be placed also at different distances. And the distance of 10 millimeter, as well as here, the distance of 10 millimeter, is used to calculate the personal doses for the whole body. So the equivalent dose for the whole body. For other organs, like skin or feet or hands, 7, so it's mistake, not 007, but just 7 millimeters is used. The distance of 7 millimeters. Oh, no, sorry. My bad. So 007 millimeters, yes. And for eye lens, for example, for doctors or for people who are working with X-ray machines, the 3 millimeters distance is used to calculate or estimate the personnel equivalent dose. If we know what is inside of our container, where, for example, in principle, we can calculate the dose rate from this source of ionizing radiation. And the simplest or easiest model is the model of just a point source of gamma radiation In this case, the dose rate will be calculated as an activity multiplied by the constant, let's say gamma radiation constant of this radionuclide, and divided by the squared distance from our source. So this simple equation can be used for, let's say, first estimations of the dose rates. Why it is just the first estimations? Because in principle, our containers are not a point sources, they are prolonged sources, and the radiation will be so let's say migrate or penetrate in different ways. But if the distance from the container is very long distance, so we can see this container as a point source. It is interesting that the dose rate created by indirectly ionizing radiation by photons for gamma rays or X-rays is not maximum, has not maximum value at the very beginning. But the kerma, so remember that kerma is used for indirectly ionizing radiation, is built up during the penetration of the ionizing radiation in depth. Because the higher the penetration range, the more charged particles are produced. And at some point, we reach the equilibrium between the number of charged particles produced and the number of photons that are scattered. So we see this build up of the number of charged particles and the build up of the kerma inside the material inside our body. And it is important for medical applications, for example, for medical cares. Photons, you can see this build up of the dose and then decrease of the dose produced by photons, by X-ray or gamma radiation with the depth, penetration depth. But photons, they don't have some final penetration range. They produce the dose in, let's say, infinite distance. But it's not the case for protons or other charged particles, because they have some finite, some limitations in penetration depth. And this is we have the consequence of this different behavior, that X-ray or gamma knives, they produce higher doses even for the tissues that don't need to be irradiated, so the healthy tissues. And this is not the case for protons, because they can be stopped just by their nature at some point, and there is no additional irradiation of the healthy tissues. So for medical care, you can see that protons may be much more preferable than X-ray or gamma rays. So now we know about the doses, how to, what are they and what they means, but what the effect of different doses. And it depends on the dose itself. Is it big or low? And did we get the dose in a short time range of time, or it is the prolonged action of ionizing radiation? And if we are talking about the high doses that people can get in the short time, then we are talking about the deterministic effects. So deterministic effects, the effect directly depend on the dose, and we can see this effect directly after action of ionizing radiation. It can be skin damage or hair loss or some cataracts or other actions. So we can see them directly in a short time. But at low doses, especially prolonged irradiation of the body will cause the stochastic effects. So it is effects that increase the probability or risks for our health, but it's not. We cannot see it immediately after action of ionizing radiation. So, in principle, these deterministic effects, again, we can see them immediately after the action of ionizing radiation, and the stochastic effect we can see after maybe few years after action of ionizing radiation. And how to get the statistic about the risks of the low doses? Of course, it is not experiments on the on humans, but it is a database about the health state of the people who work with radioactive materials, people from Japan who were bombed in Hiroshima and Nagasaki, or people who have a medical procedures with use of ionizing radiation. From all these databases, there is let's say experimental or real linear dependence on the risk of the cancer, depending on the dose that is absorbed in the human body. And it is a linear model, linear non-threshold model. So we assume that any increase in the dose will increase the risk of getting cancer. So about the deterministic effects, there's this table. So we can say that 10 grays, it is absolute lethal dose for many people. Yeah. So and deterministic effects, just to have some limit when we can say that we can observe the deterministic effects. It is 100 milligray or millisievert if we are talking about the photons or gamma rays. So it is the let's say threshold for the deterministic effect. To measure the doses, to control the doses that personnel get, we use dosimeters of different design. Very often we use thermoluminescent dosimeters. So it is they use material like lithium fluoride doped with magnesium. It is I would say the main material for dosimetry, because it is very close to biological tissue by its density and average charge of the nucleus. And these dosimeters, they produce again light, they release light by heating, and the intensity of this light is proportional to the absorbed energy, so the absorbed dose. And we can recalculate this absorbed dose in this material to the equivalent dose. So there are many other types of dosimeters that can be used for low doses or for high doses, like chemical dosimeters or radiochromic films that really used for high doses. And for online control, so all these materials, they are not, so they show you the doses not directly. You should analyze the property of materials after irradiation. But for online control, you can have some stationary dosimeters or personal online dosimeters or some mobile dosimeters to check the radiation situation in your workplace. And how to protect? So there are three main principles. First, to decrease the time. The less you work with radioactive materials, the less dose you will get. Then increase the distance, because radiation will decrease with the so it's inversal ratio to the square distance. If you increase this distance 3 times, the dose will decrease 9 times, so it's quite easy. Or if no time or no distance no time decrease or distance increase can be applied, then use shielding. And for shielding, should use different materials for different types of radiation, because again, it depends on how different types of radiation interacts with matter. So for alpha particle, for alpha emitters, it is quite easier. Just use gloves and respirators, so no radiant lights will penetrate to your body. For beta, we should not use heavy materials, because in this case, beta radiation will create Bremsstrahlung, or the stopping radiation. For shielding beta radiation, we should use light materials like organic materials or maybe aluminum. But for gamma radiation, we should use heavy materials. You see that it is important to understand what radionuclides are in your sources. So it's just representation of how different shieldings can look like. And this picture from this source, there's a link, Nuclear Power Net. It's quite a good representation of how we use different shielding materials against different types of radiation. And again, no heavy materials for beta radiation, please, because we will produce Bremsstrahlung, that means X-rays, and we will irradiate ourselves from the shielding. So, and brief conclusion. So, ionizing radiation is everywhere. Again, as I mentioned earlier, we have radionuclides, air, our meal contains radionuclides, so they are everywhere. But this ionizing radiation can be harmful if the intensity of this ionizing radiation is above the limits. The 3 pillars of radiation safety, again, justification, a lot of principle as low as reasonably achievable, and the use of those days. It is good to understand that we cannot measure these protection quantities like equivalent dose directly. We can estimate them only by converting the measured physical or operational quantities. And we should remember that different types of radiation have different biological response, and different tissues has different sensitivities. And depends on the doses, there are different effects. And I hope that in our life we will say only about the stochastic effects, because it's low doses. And to estimate the risks or the probabilities of negative effects of the low doses, we use the linear non-threshold model or theory. So to estimate the effect of the radiation work conditions, we should use dosimeters. We should estimate the personal dose, equivalent doses, and if necessary, we should use shielding as well. But it is important to remember how different types of ionizing radiation interact with matter to choose the proper shielding material. So that is all for this lecture. Thank you for your attention, and yeah, I'm ready to answer questions, if any.
Dear colleagues, we are finished, so we are waiting Olga and go to the